Hello and welcome to a review session for the Coding Club. This session will be for CSCI 232, Computer Organization. The format of this review is going to be just a quick explanation of certain parts of the course. And we're not going to cover everything, just go through the slides quickly, explain some important concepts, and move on to the next one. This is kind of a loaded course, so I'll do things quickly to not take up too much time. So the first part of the week 1 slides takes you through the journey of a high-level program, like written in C, for example, and how it gets converted into something that can actually be executed by the computer. So you have this C code, and this is hash include standard io.h. This is a reference to an external library, or a system library in this case. And this file, standard.io.h, contains declarations of specific functions that you will be using in the program. For instance, printf in this case. Okay, just declarations, not the actual implementation. Now, you have your program here, and the preprocessor is going to go look at this include statement or include directive and place its entire contents into this file. So all the declarations of the functions that are in here, like printf or scanf, are going to be put into this file. So now you have like the modified source program, which is completely C code. The compiler is going to take that and turn it into an assembly program, and the assembler is going to take that and convert it into machine code, or specifically relocatable object program. And this object program contains references to those functions that are in here. However, the implementations of those functions, actually they're stored in a certain part of the system as relocatable object files as well. And so the linker is going to take those as well as the program that you wrote here, and it's going to put everything into a single executable program. So you're going to have your printf.o file, which contains the actual machine code that performs the printing function, and you have your program here. Together you have the executable. Now this picture should be clear to you since you've presumably taken the course and paid attention. There's a few details that are later in the course that clarifies this picture, but at the start it's okay if you don't fully understand what happens here. Anyways, compilation, you can do GCC, which is a compiler more or less, -o hello, so name the output file as hello, and take as input hello.c. You can also do this the other way around. You can say gcc hello.c -o hello, doesn't matter. And then to execute the program, you can do /hello. Now this is only going to work if you're in the same directory as the hello executable, but anyways. Now the reason you need to understand why the system works is because if you don't know how a compiler works, how it does its job, well, you're not going to be able to reliably write good C programs that the compiler can optimize and like do things properly in general. And another thing is that there are certain pitfalls when programming in C that if you don't know how the system works, you're not going to be able to realize what you did wrong. So even though the the code seems to look fine, when you actually execute it, even if there's no compiler errors, you're gonna get some problem. Anyways, in this course, you're gonna learn x86-64 assembly. And this is used by recent-ish systems. Yeah, so this course covers x86-64 assembly, and that's used by recent-ish systems like most computers using Linux and Windows. Nowadays, Macintosh uses some other architecture. Don't worry about that. And importantly, you're going to learn how compilers map certain C codes into assembly language. You're going to take basic stuff like dealing with variables, think a little bit about arrays, multiplying, adding, subtracting, dividing, shifting as well, and performing certain operations that allow you to deal with memory. But there will be nothing about like printing text because that's actually even somewhat more complicated. Anyways, the hardware organization of the system looks more or less like this. There's a few different points in more recent computers, but this is pretty good for a mental model. So you have the CPU here, the registers, RAX, RPX, RCX, RDX, RDI, whatever else. You have the ALU, the arithmetic and logic unit, which performs certain computations on the data in the registers and puts the results back into registers and so on. And in doing so, it also alters certain flags, which are also in a certain register, but they're treated separately. They're useful for certain branching instructions as well as yeah, branching in general. You have the PC, the program counter, which contains the address of the next instruction. And you have the bus interface, which which lets the CPU actually load data in and out and move things out into the main memory and to the I/O devices. Now, that hello.c program, the hello executable, where did we go? When you want to execute it, you're going to type ./hello, right? And that's going to go in through the keyboard, which is a type of I/O device, as you know, input-output. It's going to go through to the CPU, and the CPU is going to store that into the main memory. So it knows now, it has memorized that you have written hello. And then when you execute the actual file, it's going to go and load it from the disk into the main memory. Now, it's possible, actually, originally, it would get loaded through the CPU, and the CPU would put things into the main memory. But more recently, somewhat, direct memory access has been a thing, and that allows for I/O devices to directly interface with the main memory, and the CPU would have very little work to do here. It would only require initiating the I/O operation, but after that, it doesn't need to manually move every word into the main memory and back. So that's nice. Anyways, so now you have the hello object code. It's gonna get loaded into the CPU, into the registers. The CPU is gonna process it. And then the outputs are gonna be taken through the buses to your graphics adapter and into your display, your screen or whatever, and you're gonna have the hello world text printed. Easy enough. There's a few details that are not covered, but there's no worry. Now, notice how far the CPU is from the main memory. There's some distance that data needs to cover and go into the CPU, and the other direction as well. On a time scale that is ordinary to us humans, like seconds or minutes, this speed is insanely fast, the order of microseconds for data to go back and forth. However, for the CPU does all its operations on the order of nanoseconds. So this stuff takes thousands of cycles to do, or hundreds of cycles. Therefore, there's a need for like smaller memories, which are called cache memories. And these are closer to the CPU, so the CPU can interact with them more quickly. And usually you have three levels. You have the L1 cache, the L2 cache, and the L3 cache. All of these are of the type static RAM, static random access memory. The L1 cache and the L2 cache are present one for each core of the CPU. And then the L3 cache is shared by all the cores of the CPU. The L3 cache is the largest, and basically the caches contained like the most recently used data, and things are loaded into the L3 cache, then L2, then L1, and into the registers, and back and forth. Now, the CPU is gonna check like first what's in the L1 cache. If it's not there, then it's gonna check the L2. If not there, the L3, then main memory. Easy enough. Now, onto Amdahl's law. Now, this basically lets you figure out the overall speed up of a system when you speed up only a specific component of it. The formula is given here. Keep in mind, all of this is in the denominator, despite how it looks. So you have 1 divided by 1 minus alpha, where alpha is the fraction of the time taken up by the component, plus the alpha divided by k, which is how much you sped up the component by. So 1 minus alpha represents the amount of time taken by the rest of the components, because this component takes alpha time, so the rest of the components must take 1 minus alpha time, right? Then for the time of alpha, the component is gonna get divided by some amount, and so you take all that, and this is the new time. Then the speed up is just 1 over that. Easy enough. You have an example here if you want. Now, next is concurrency and parallelism. Concurrency, basically, it's when you have several tasks at once and you want to execute them. In the most basic form, when you have only a single core, you're gonna have several tasks, let's say tasks 1, 2, and 3. And you're gonna process a little bit of task 1, then a little bit of task 2, then a little bit of task 3, and go back. That's one example of concurrency. However, when you have concurrency and you have multiple cores, you can make use of parallelism, which is basically assigning each of the tasks to a different core and making things process faster, more or less. Okay. Now, parallelism has several types. You have the thread level stuff, you have the instruction level stuff, and you have SIMD, which is like a single instruction in assembly or machine code that operates on several pieces of data all at once. And these are at several levels. You're not gonna see this in detail in this course, I believe, but for those taking computer architecture, which is computer science and computer engineering majors, you're gonna see all of that. Unix, just quickly, it's an operating system. Mac OS is based on Unix, and so is Linux in some way. However, Linux does some stuff and evolved away from that. Mac OS is more or less like vanilla, with a bunch of extra stuff. Anyways, history you don't need to know, and I probably got that wrong anyway. Command line, something really important that you need to understand how it works. Now, the GUI, you have like all these different folders. You can click the files. I did not just try to open that. And you can go into other folders. You can click a folder to go into some other directory and so on. Now, with the command line, you use commands to do all of this. Now, just looking at these files, they're displayed in front of you. But in the command line, you can do ls on Unix and Linux to display the file names of those files. So you have all these files here, and similarly, they're displayed all here. Okay. Now, the reason you do this is that all these GUI interfaces are pretty different from each other. And so it's better if you stick to this because it's more familiar and more or less standard. It's present almost everywhere. So no matter, like, most systems are gonna have the same command line tools, if you will. Next, these are some commands you can try. You're not gonna get tested on this, I believe, but you should know these anyway. Dealing with the command line is, believe it or not, really good because you can only do so many things with the GUI, but with the command line, you can actually, like, set up scripts, essentially programs that do all of these things at once, execute like different perform different tasks without you having to do any of this, like, step by step. Okay, open this folder and that folder and that. You can just run the scripts and everything happens. Next, you have the C program here. Now, to take CSCI 232, you need to have taken CSCI 112, which is Introduction to Computer Programming in C++. And C is, the syntax is more or less familiar to you already, but there's a few differences. In the case of this course, the main difference will just be that you use printf and scanf for input and output and input respectively, rather than cin and cout. Cout and cin. Okay. Comments, you know how to do those. Imports, yeah, you have the library. Same deal. You're using standard io.h instead of iostream. What else? Yeah, this is some mindset stuff. Basically, why do you need to understand this computer organization topic? How the system actually works, how computers work at, like, the somewhat lower levels of abstraction. So you have the hardware here. System software allows you to interface with that hardware. This includes programs like the operating system, let's say your compiler, your device drivers, which let you interact using the keyboard and so on. And then you have the application software, which uses the tools provided by the system software to do some other tasks. So this picture is pretty important. The hardware level, you have all the stuff. Then you have the instruction set architecture, which is basically the design, more or less, like what do you need to know about how the processor works in order to write assembly programs. And so this defines like the actual instructions, the assembly instructions or the machine code instructions that you actually use when programming in assembly or machine code. And how do you use them properly? What are the syntaxes available to you? And above those, you have all this different stuff that makes these programs actually useful and also easier to interact with. So yeah, you have the instruction set architecture abstractions. So you have this C program is going to get compiled into assembly. This is how assembly looks, more or less. You have the instruction, you have the arguments, also known as operands, and usually these have a source and a destination. Like the result of this, like this is a multiplication instruction. The result of the multiplication of register 5 with 4 is going to be placed into register 2. I believe that's what happens. I'm not really familiar with MIPS. So yeah, you have all these different instructions. In the course computer organization, again, you take x86-64, which has similar instructions, but they have different, like, different mnemonics, and the registers are also named differently. So here you have all these different registers up to register 31 apparently. But Intel has only 16 registers available to you, I believe. General purpose registers. We've seen the compilation process, and there's a reminder here that if you want to do anything with Linux and so on, go to the networks lab or get a local installation. We've seen all of that already. Memory, yeah, memory is finite, and C and C++ programs allow you to mess with pointers, which let you directly access memory. And so you need to understand properly how these things work and not deal with them just like carelessly, in order for not only for your program to be correct, but also for your compiler to be able to optimize things properly. Finally, the cache memory, as mentioned, is closer to the CPU, and so it's way faster. So if you're able to write programs that make use of the cache memory, you're gonna get much better performance. Second. Okay. So about performance, op count is basically like the number of atomic operations that are performed by the program, by the CPU. So you have each instruction basically is a single operation, but that by itself does not predict the performance, because these instructions may these operations may take different amounts of time, and in abstract, like higher level algorithms courses and so on, these instructions are just assumed to have the same runtime, because you're dealing with things at like a higher level of abstraction. You don't care about the little stuff that's not going to take more than some constant amount of time. But to get actual good performance on a real world system, not just theoretical one, you need to understand this stuff. Okay, so yeah, you need to understand like what sorts of bottlenecks can happen, like we said with the main memory, because it takes so long for things to go back and forth. So you need to be able to exploit the cache memory and so on. And yeah, you don't want to go too far with optimization and make your code hard to understand. So that's another thing. Yeah, this is not a problem. The assembly code view is that the CPU has registers, the program counter, and the condition codes. So these are all the data basically available to you within the CPU itself. The condition codes, I believe we mentioned earlier, that when performing certain arithmetic or logical operations, some information about those operations will be stored here. So for example, the when you perform an addition and it causes an overflow, like if the result is too big to be stored within the register, then a certain flag here will be highlighted. You can check that flag and then make your program react according to its value. And yeah, in the main memory you have the code, the actual instructions, you have some data, and you have the stack, which contains like certain variables, and also the return addresses for, like for functions when they're called and stuff like that. Anyways, yeah, stack to support procedures. Anyways, instruction set architecture, we've already described that. And finally we have RISC and CISC. RISC is reduced instruction set computer, which is basically like the instructions that are available to you when programming an assembly. Like the instruction set architecture is limited to very few types of instructions, and they're very basic, very simple. And because of that, they're actually quite fast at executing separate instructions. Meanwhile, with CISC, these have hundreds, even thousands possibly, of instructions. Each one has like a specific task, possibly. They're very specialized. They can act on like multiple operands, not just two or three. You can have as many as five. And Intel CPUs are of this kind, and things like RISC-V, MIPS, and I believe ARM are all RISC processors. So some differences here are listed. The instruction set is very large, lots of different instructions. You need to learn if you want to program in a CISC architecture. You need to know all these instructions, when to use them for the highest efficiency. Meanwhile, with RISC, there is not many you need to learn, but you need to understand like how to put them together to write a fast program. A single instruction in CISC takes a while because they're specialized. They can do things like calculating the square root. So this takes a while to calculate. The CISC processor does this for you, but instead of you having to write like 10 or more instructions to do that, the CISC has an instruction for it, but it's going to be really, really slow, taking many cycles. Okay, what else? Code expansion is not a problem, which means basically that the code is pretty compact in that it's pretty short, not many instructions. Meanwhile, with RISC, because you have to have all these multiple instructions chained together to perform any complicated task, that can be kind of problematic. In CISC, the decoding of instructions is complex, whereas in RISC, the decoding of instructions is simple. This means the structure of the syntax and so on, how the CPU understands them, varies between CISC and RISC. CISC requires external memory, while RISC does not. And CISC has only a single register set, while RISC has multiple register sets. Okay, easy enough. That concludes week 1. We've taken 22 minutes so far. That's a good pace, I guess. And see you in week 2, I guess. Okay, so moving on to chapter 2, which is on bits, bytes, and integers, and how integers are represented in binary format, and also how to work with these binary numbers. So, yeah, several types of representations of integers. You have the unsigned, which is 0 and positive numbers only, and you have the signed representation, which can deal with negative numbers. You have methods of converting between the two, between decimal and binary, between hexadecimal and binary, and so on. And casting, which allows you to go between these two in the C language. Expanding, which is adding more bits to the representation. Truncating, which is removing bits from the representation. And what happens to the value when you do these operations, and a little bit about what these bits and bytes actually can be interpreted as. So binary numbers are, you should know how to count in binary by now. 0, 1, 1, 0, 1, 1, 1, 0, 0, and so on. Hexadecimal numbers are like a more compact representation of them. Because the base here is 16, and 16 is 2 to the 4. And because of that, you can take each 4 bits of a binary number and interpret that as a single hexadecimal digit, if you will. Okay, so for example, you have this number 0011, 1011, 0110, 1101. You can group them 4 bits. You can group them 4 by 4 bits. So from the right side, so the first 4 bits from the right are going to be grouped together. This gives you a D. Next 4 bits are 0110, which are 6, and so on. And these are the data representations. A few important points are that the 32-bit machines have the long integers as 4 bytes, same as the ints, and pointers as 4 bytes instead of 8 bytes, which means they can only address up to around 4 gigabytes of addresses rather than whatever that number is. And yeah, doubles are still 8 bytes or 64 bits, even on 32-bit machines. These are some notations for converting between like a typical binary bit vector into the signed representation or into the unsigned representation, from the unsigned representation into a bit vector or into the 2's complement, and from the 2's complement into either the binary bit vector or the unsigned. So the T and the U are decimal numbers, essentially, and B is the actual bit vector that represents the same number. And we're also going to take a look at the min and the max values given a W bit vector, like a bit vector of length W bits. Okay, so you know how Boolean algebra works, I'm sure. The OR operation is 1 whenever either of the bits is 1, as represented by the table on the right here. It's a mistake in the slides. And the AND operation gives you 1 only if both of the bits are 1, not flips from 1 to 0 and 0 to 1. And XOR gives you 1 whenever the two bits are different, and 0 whenever they are the same. Boolean algebra on bit vectors is applied bit by bit. So when dealing with this here, you're going to take a look at the rightmost bit on each one. You AND it, and you get a 1 here. Then you take the second bit, AND it, and you get a 0, and so on. Same works with the OR, with the XOR, and with the NOT. And this is an example on how the AND, the OR, and the XOR can represent operations on subsets, which is a more mathematically oriented example. So not really central to what we're learning here. In the C language, these operations use the ampersand, the vertical bar, the tilde, I think, and the caret. So this is the AND, the OR, the NOT, and the XOR. And also, you should be getting a question on this in the exam. When you want to convert, when you want to do these operations on hexadecimal numbers, you first need to convert them into binary, and then perform the operations, and then convert back into hexadecimal, according to this table here, right? And this is true for even the AND and the OR operations, not just the NOT, okay? Now, do not confuse these operations with the logical AND, which uses 2 ampersands, the logical OR, which uses 2 vertical bars, and the exclamation mark, which is the logical NOT, okay? They behave differently, as described here. Now, shift operations, when you shift left, you get rid of all the bits on the left side, according to how many bits you're shifting, how many bits you're shifting by, and on the right side, you fill by zeros. Now, for the right shift, there's 2 versions. First one's the logical shift, and the second one is the arithmetic shift. With the logical shift, you always fill it with zeros on the left side, and with the arithmetic shift, you take the most significant bit and fill with that instead. So if it's a 0, like in this case, it's going to behave like the logical shift. But if this was a 1, you're going to get a 1 here, 2 1s here. And keep in mind, shifting is not defined for negative numbers or for numbers greater than the word size, like 32 or 64. And this is how to convert from positive to negative and from negative to positive in the 2's complement representation, which is the signed representation. So when you have a number like this, if you want to convert it to when you want to invert the sign from 15,213 to minus 15,213, you look at the binary representation, you flip all the bits, so the 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 1 becomes a 0, and so on. And then after that, you add a 1. So let's do an example. Well, this same example, but let's show exactly what happens. So this is our number, 15,213, and we want to get minus 15,213. And the result of that is if we invert every single bit by 1. So the 2 zeros become 2 ones, 3 ones become 0, 0, 0, 0, then 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. And then you add a 1. In this case, adding 1 is just like this, but if we had already 1, 1, then we'd get a 1, 0, 0. Okay? So the result should be this. And if we check the PDF again, that's exactly what it is. And yeah, for the signed representation, keep in mind the most significant bit has a negative weight, okay? So looking at this, the rightmost bit has 2 to the 0, this is 2 to the 1, this is 2 to the 2, this is 2 to the 3, this is 2 to the 4, but in signed representation, the 2's complement, it's actually minus. And that's it. That's all you need to know about the 2's complement, essentially. Everything else just works out once you have this thoroughly in your mind. When you want to convert decimal numbers into binary, you want to divide by 2 and then check the remainder. 15,213 divided by 2 is 7,606 with remainder 1. The remainder 1 goes here. And then you take 7,606 divided by 2. You get a remainder of 0. And you put the 0 here, and so on. You keep dividing by 2 until you have exhausted the number of bits here. So we want to represent it with 16 bits, so we do 16 divisions and we stop after that. So this is especially important for negative numbers, otherwise you can just keep going forever. So in this case, you get, after stopping at 16 bits, 16 divisions, you have all of these bits. So this one goes here, and this one goes here. Okay, moving on, numeric ranges, yeah. With unsigned, the smallest value you can represent is 0, and the maximum is 2 to the w minus 1 when you have w bits. And when it comes to the 2's complement, the lowest value is minus 2 minus 2 to the w minus 1. And the maximum is 2 to the w minus 1 minus 1. And if you add these two together, you're gonna get minus 1. Like this and this are gonna cancel. The result is minus 1. But in the binary representation, it's gonna be all ones. And that's why you have all ones here. These are some values for the word sizes given w's of different values. Now this is a bit on how you count up in unsigned and signed. When you have 4 bits, you're gonna go 0, 0, 0, 0, 0, 0, 0, 1 up to 0, 1, 1, 1. This means the T max, which is the highest signed value, which is characterized by having a 0 on the left side, then all ones on the right. Okay. After this, the next binary value is going to be 1, 0, 0, 0. And for unsigned, this is just an 8. But for the signed, it's going to be minus 8, because this has a weight of minus 8, and then the 4, the 2, the 1 are all zeros. And then when you count 1, 1, 0, 1, 1, you're going to be adding to that minus 8. When you have 1, 1, 1, 1, you have minus 8 plus 4 plus 2 plus 1 equals minus 1. Moving on. Yeah, this is what we just saw essentially. No worries about it. Typecasting is when you convert from signed to unsigned and unsigned to signed in this case. You can convert from other types as well, but anyways. To convert from unsigned to signed, you use int within parentheses, than the unsigned variable you have. Similarly, from signed to unsigned, you do unsigned and then the variable's name. And yeah, you don't need to explicitly do this always. You can, it happens implicitly in certain cases. Now, when you want to expand the number of bits in a certain bit vector, if you want to maintain the same value, like this W bit vector of which is X represents some number, some decimal number. If you want to maintain that same number after adding multiple bits, so this X prime here with all its extra bits still represents the same decimal number. What you want to do is take the most significant bit and copy it everywhere here. Okay? So if this were a 1 for a negative number, all of these will be 1s, and thus you will get the same value in this representation and in this representation. X and X prime will be equal. So yeah, for example, 0, 1, 0, 1, 0 extended by 1 bit, you just get an extra 0. And when you have 1, 0, 1, 1, 0 extended by 1 bit, the 1 gets copied onto the left side here. Same deal when you're converting from short to int, so from 16 bits to 32 bits, it's gonna sign extend, and same with the negative numbers, it's gonna sign extend here. Okay. When it comes to truncation, when you're removing bits, you just remove them, nothing else, and then you interpret the new bit vector as possibly a new number, because it depends on what these values are as well as the most significant bit. It might change the number, it might not change the number, but it will depend. So here's a few examples. Essentially, what you want to do, just cut the number of bits, and then interpret the new number again. One way to do it is using the modulo method, though it's not really necessary, just use your brain. So that's it. In C, we've already seen all of that, don't worry about it. Now in memory, the memory is represented essentially like a really long array. You can abstract it in this way, have a good mental model of it like that. And an address is the index in that array. So this is index 0, this is index 1, index 2, index 3, index 4, up to index all ones. Okay. This is obviously unsigned, but anyways. The system provides private address spaces for each process. Okay. This means that the running program, the addresses it has available to it are completely separate in a sense from the addresses available to other running programs. Okay. The same address for a certain program can be referring to a different thing in a certain other program. Like for example, address 5 in the first process and address 5 in the second process are two different things, because these processes are entirely separated in memory. This is a form of protection because yeah, programs can mess with their own addresses, their own data as much as they want, but they're not going to affect other processes' data. And yeah, most machines nowadays have 64 bits as a word size. Huge amount of addressable memory, but you're rarely going to see that. And they're represented in this way. So this is address 0. This is address 8, which means byte number 8. So it starts at byte number 8. So you can take this as like the first like the 8 bytes starting at address 8 and going up to address 15. Okay, we've seen that already. There's a new one here, long double, which doesn't exist in 32-bit, but in x86-64, either 10 bytes or 16 bytes, whatever that means. Depends on the implementation, I guess. Now, there's actually two conventions. One of them is called big endian, and the other is called little endian. Now, when it comes to the big endian, the most significant byte has the lowest address. So when you have a number like, okay, here's an example here. When you have a number 0, 1, 2, 3, 4, 5, 6, 7, the 0, 1 is the most significant byte, right? And this is gonna have the least address, in this case 100. But with little endian, the least significant byte, the little end, is gonna have the smallest address. And that concludes chapter 2. Okay, so now floating point numbers. First thing is that there's infinitely many real numbers, even within a small range, like between 0 and 1. So you can't actually represent all of them with a limited number of bits. Therefore, you need to approximate them using that limited number of bits. And one way to do that is using the fixed point representation, in which you have you have some number of bits representing the integer part of the number, and some other number of bits representing the fractional number of part of the number. So in this case, you have 4 bits for the integer, 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0. And then for the fractional part, you have 2 to the minus 1, minus 2, and minus 3. So that's 7 bits in total. But it turns out that this is kind of limited, because you don't actually know what's the best place to put the point, right? So the floating point representation comes in and solves this issue, basically. And what it does is follows something similar to scientific notation. So in scientific notation, you had x times 10 to the y. In this case, you have x times 2 to the y, okay? And this is how it looks. You have the sign bit, you have 2 to the y, with y being the exponent, which is 8 bits. And then you have x as the fractional part, which is the remaining 23 bits. And the exponent, notably, actually represents, okay, so you take the 8 bits of the exponent and you subtract minus 127 to get the actual y value here, okay? The actual value that the x is being multiplied by. Okay, so you also need to keep in mind that when the bits are all zeros or all ones, those are reserved values and they have special meanings. Now, another thing is that the fractional part actually squeezes out basically one more bit, in that when you're representing when you're representing fractions in binary, the number to the left of the decimal point is always a 1, okay? So you can just assume that there's a 1, and then have these 23 bits represent the rest of the number, the actual fractions, okay? So then, this is, scientific notation in decimal, as I'm sure you've seen many times before. And in floating point, okay, this is fixed point somewhat first. So 18, the integer 18 is 10010, which is 2 plus 16. And then the 0.5 is like we saw with the fixed point is 2 to the minus 1. So we have the 1 here, okay? Now, to put this into floating point, you need to move the decimal point so that it appears after the most significant. This means that the point basically moves to between the 32 and the 16 over here, okay? And then, so you would have 0.100101. And then because you shifted it by 5, so you divide it essentially by 2 to the 5. So you need to add a multiplication by 2 to the 5. Okay? So we shifted it by 5 to divide by 2 to the 5, and then we add multiplied by 2 to the 5 to get 18.5 again. And that's basically how the floating point representation works, but there's a few things to keep in mind. In that certain numbers can't actually, again, this is an approximation, so certain numbers can't be represented with a finite number of bits. So when you want to convert a fraction into the bits, like in the binary representation, you multiply by 2 instead of dividing by 2, which was done for integers, okay? So you multiply this by 2, you get 0.75, which is less than 1, so you get 0. Then you take that 0.75 and you multiply it by 2, you got 1.5. Now 1.5, you take the 1 and take that as the point here, okay? So this 0 went here, and then the 1 from the 1.5 went here. And then you take the 0.5 that remained, you multiply it by 2, you got a 1 again. That goes here. And then the 0, no matter how many times you multiply it, you get zeros every time. So it's sufficient to use 3 bits to represent this. But if you had something like 0.376, you'd be stuck multiplying forever. And so you need to stop at some point, which is the 23 bits that we saw here, okay? Moving on. We don't need to look at that. We have, okay, this is important to keep in mind. Single precision is what we saw. You have 1 bit for the sign, 8 bits for the exponent, and 23 for the fractional. For double precision, the double data type, let's see, you have 11 bits for the exponent and 52 for the fraction. For extended precision, which is 80 bits, you have 15 bits for the exponent and then 64 bits for the fractional. I'm not sure why it says 63 here. You can check the standard or the Wikipedia page. There was some explanation, I just don't remember it. So yeah, now we'll see an example of how to convert. So for the integer part, you convert it into binary as you saw before. Same idea as in the previous lecture. You take the remainders, and the first remainder is going to be your least significant. Then the next remainder is going to be the next least significant, and so on. Or alternatively, you can keep going until you get a 0, and then read them with the last one being on the left side and the first one being on the right side. Whatever you want to do. And for the decimal part, you multiply it by 2, and whenever it exceeds 1, you put a 1. Whenever it doesn't exceed 1, you put a 0. That's not really explained well, but with the example we saw above, I went into actual some level of detail. Anyways, so now you have the integer part from the divisions and the fractional part from the multiplications. Put them together as like a fixed point representation. Then move the point all the way here and multiply by the same exponent. Okay? So that gave you 1.0101010001 times 2 to the 6. And the 1 is assumed to be there. That's why you move the point to right after it. I believe that's how it works. So you assume that it's there and just take the fractional part and put the exponent, add 127 in the case of single precision floating point, and you get 133. And 133 in binary is this 10000101, okay? And put that into the exponent. Floating points in C, yeah, you have the floating point type, which is float, and the double precision type, which is double. Yeah, easy enough. And that concludes this chapter or lecture. Okay, so moving on to the next lecture, Introduction to Assembly, which is week 4. Most of this is just some history stuff. You can, it's mostly for your own information and will not be covered in the exam, I believe. For assembly, so you're given a C function and you're given how it looks like in actual Intel assembly x86-64. This is a specific syntax. I don't remember its name. Don't worry about it. There's several others. Now, this is the move instruction, which moves, in this case, the value, immediate value 0 into the register EDX. And this does the same thing, but moves it into EAX. And then this is an unconditional jump, which means it sets the program counter to be equal to this value. And so the next instruction to be executed would be at this address. You see that? And it's going to be executing that. Compare ESI with EDX. And after that, it's gonna execute this instruction, which is jump if less than, which is like a conditional jump. If the comparison did something, had a certain value, a certain result, then jump to 4005 C2, which is here. And that's going to perform the actual, sum plus equals array I operation. Easy enough. Now, we're gonna take all these instructions properly later, but that's the main idea. Now, instructions have a name, and that's also called the opcode. The opcode is actually just the binary representation of it. And then you have the operands, which are the things that the instruction acts on. These are like arguments in the C language. When you have a dollar, this is an immediate value, like just a number. And when you have a percent sign, that's the name of a register. Okay. Yeah, that's fine. These are the Intel registers. You have RAX and all the other ones. RBP is the stack base, and this is the this is the base pointer, and this is the stack pointer, I guess. And then you have these extra registers from R8 to R15. Now, importantly, these are actually like the 64-bit versions, and each one has like several names that represent like a 32-bit subset of it. Like, for example, we had EDX, right? This is actually just RDX, but the 32 bits on the lower end of it. Okay, next is, yeah, we've already seen that. So when you have a statement like this, int sum equals x plus y, first you need to load x, then you need to load y, then you need to load to add the two numbers, and then store the result somewhere, which can be in x, can be in y, can be in a third register, whatever you like. And after that, you write the result you take the result of this sum, which is now in the sum register, and you put the value in that register back into memory, and that place in memory is represented by sum here. Moving on. The move instruction just copies things from one place to another. And the first thing is the source, and the next one is the destination. Okay, this is the most basic syntax, but there's several others that we will see. The source and the destination. Okay, the source can be an immediate value, like just a number, or it can be a register, or it can be a memory address, and that's the source. For the destination, it can't be an immediate value. How do you move a value into a value? You can only move values into places like registers and memory locations, you see? Now, importantly, you can't move from a memory location to another memory location directly. You need to first move from memory into register, then from register into memory, into some other memory location. So the first syntax is just source comma destination, but there's others. And when you put the parentheses here, this means you're using RBX as a pointer, which means RBX contains some address. You go to the address and take the value there, and then you put it into the destination. And in this case, whatever this value is, go to the address given by RBX. So go to that place in memory and put the value into that place. Okay. Next, you have a displacement or an offset. And this is only done with when you're addressing, like when you're doing the parentheses to access a memory address. So when you put an immediate value before this, you basically have REX, add 10, and then go to that address. Okay. So suppose REX had 100 hexadecimal value. 100 plus 10 is 110. And then you go to that address, you take the value in it, and you put it in whatever this destination is. And same idea, take the value and go to address 110 and put the value there. And another way, another syntax is to have two registers. Now, the first one is like the base, and the second one is like the offset. Basically, you add RAX to RDX, you go to that address, so the address RAX plus RDX, you take the value in that address and you put it in the location, in the destination. And this is the other way around. And then you have the immediate, displaced or the offset with the indexed. Okay. So you take RAX plus RDX plus 10, and you'd go to that address, you take the value there, and you'd put it here. And there's one more syntax, kind of, which is when you multiply, okay, when you have like a number here after the second comma, this means multiply this number by this register, add it to whatever the initial register was. If there was anything, you can have nothing, so this is just 4 times RDX as the index. Go there and copy the value into the destination, and this number can only be at 1, 2, 4, and 8. And all of these are like different mixes of that. So this is the most general and most complicated one, which is RDX times 2 plus RAX plus hex 4. Go to that address, copy the value, put it into the destination register. So yeah, the most general operand form is immediate, followed by the base register, followed by the index register, and the scaling factor. And the scaling factor is multiplied by the value in the index register, then added to the value in the base register, and added to the immediate value. And yeah, the immediate can can also be negative. You can have this equal to 0. So you can have parenthesis, left parenthesis, then comma, then the register and the sum and the scaling factor, sorry. And you can also have just the base register. So yeah, that's about it for the move instruction. You have a few exercises here. So let's do them. First one is move 0 into register RDX. Second one, so this means that RDX equals 0. Like whatever variable is represented by RDX. It can be like some variable int x or int y or int whatever name. Just set it equal to 0. And then you have move RDX into RCX. So move the value in RDX into the location, this register, RCX. This means, suppose RCX is the variable x in C, and RDX is a variable called y. This instruction is equivalent to saying x equals y. Next, move immediate value 42 into the address pointed to by RDI. Now in C, you probably haven't really studied pointers at this point, maybe. So this is essentially let's go into the text editor for a second. We had this, right? So this, suppose RDI is the register representing a variable called x in C. Okay. Oh no, because this is an address. Let's say it's a pointer instead. Okay. Called p. Okay. So percent RDI is just the value in p, and then in parentheses percent RDI is star p, which is the value in the address contained in p. That means p contains an address. You go to that address in memory, and the value in there is star p in C, in the C language. Now, what this is saying is star p equals 42. Move the value, immediate value 42 into star p. And so this is going to go into memory wherever p is pointing, and set the value there to 42. Okay. Finally, we have move RAX RCX 8, comma, percent RAX. Okay. Now this one's kind of complicated because of the 8 here. But basically, this takes RCX, the value in it is multiplied by 8, then added to RAX, and all of that is used as an address to go into memory, and the value in there is taken and put into RAX. Now the thing about this is that the scaling factor here actually depends on the data type that you're using. So you might be using like an int or a long or whatever. And so this can be kind of problematic. to translate into C directly, so you're not really expected to know exactly how to do this. That being said, if I were to solve it, let's give it a shot. I'm not 100% sure on this, but I'll try it anyway. So we have move that into that. Now suppose that okay, so RAX is the base register. Not the base register, like the base of let's say some array. Okay. So you have like long, okay, because I'm saying long because it is 8 here, the scaling factor. Therefore, the data type must be 8 bytes long, okay? So long array. So our array here is like just a pointer to a long variable, and then RCX is like the index into that array. Okay, now another way to do this is just like that. So array of, let's say RCX represents an integer I. Okay, array of I. The value in array of I, and remember that the 8 is used to go like jump 8i bytes. So you jump 8 long values because long is 8 bytes. Wait, I long values because long is 8 bytes. Okay. So array of I is copied into the value represented by RAX. So supposing RAX is a variable x, this instruction is equivalent to x equals array of I, whatever I is. And that's it basically. Okay, so now we have the arithmetic and logic instructions in x86-64 assembly. So we saw the move instruction previously, but we only covered the basic syntax of it. And we saw all these different forms and what they mean. It's totally fine. So in x86-64, you have a few terminologies that you need to be aware of. A byte is, as you know, 1 byte. A word is 2 bytes. Now, keep in mind this is different from the word size of a machine. The word size is like how many bits the computer can operate on at a time. So for x86-64, the word size is 64 bits. And so that's the that's what word means in that context. However, when it comes to programming here, a word is 2 bytes. So keep that in mind. Double word is 4 bytes and the quad word is 8 bytes. And in x86-64 assembly, B, W, L, and Q represent like these different sizes, okay? And you're gonna see these at like on the different instructions. And these are all the different registers. So you have RAX, which is 64 bits. And then the lower order 32 bits are called EAX. The lowest order 16 bits are called AX. And the lowest order byte is AL. And every register has like all these different names for its smaller counterparts, or smaller like components, we can say. So keep that in mind. Next is the register responsibilities. You need to keep in mind, firstly, that RAX return is the return value of a function. So your main function, for example, in your C program, is going to have a return 0, for example. And so it needs to load 0 into RAX and return that using the ret instruction. Then we have RDI, RSI, and RDX, which are the parameters of the functions. So when you call a function, first you need to load values into these parameters, into these arguments. And once the values are in these registers, you're gonna call the function using a jump instruction or something like that. And that function, its assembly code will assume that the parameters are in these registers, okay? So it's the caller's responsibility to put values into here, and then the callee will deal with them. And then the callee, its responsibility, the function that was called, its responsibility is to put something in RAX. And then the caller can use this value after it returns from, after the control returns from the callee. We also have the RIP register, the instruction pointer, otherwise known as the program counter, which, as you know, stores the address of the next instruction, and RSP, which stores the address of the current top of the stack, which we will see later in more detail. Now, we saw BWLQ earlier, and so you have the move instruction with several suffixes. You can have BWLQ, move B, move W, move L, move Q, okay? And these only update the specific like sizes. Like for example, if you're doing move W to move this word R11W, this 16-bit register, into R12W, you'd use move W, and the rest of the registers will not be affected. So the upper order 48 bits, are not affected by this move instruction. However, there is an exception. Move L, which acts on double words or 32 bits, it will set the higher order 4 bytes to 0. That means if you do move L from R14D to R15D, the upper order 32 bits of R15 will be set to 0. So keep that in mind. And these are some examples. Here you're moving 32 bits, so you use move L. Here you're moving something into a DX that's 16-bit register, so you use move W. Here you're moving two hexadecimal digits, which is 8 bits, into an 8-bit register, so you use move B. And this is just an address, and the destination is a single byte, so again move B. And this is RAX, which is 64 bits, you use move Q. And then this is DX, which is 16 bits, so you use move W. Next. Yes, like we said, this is move L, this is move W for the DX, which is a word, move B for BL, move B for DL, move Q for RAX, and move W for DX. And there's other move instructions as well. One of them is the move absolute Q, absolute, ABS, whatever, instruction, and its source has to be an immediate value that is 64 bits, okay? That means you have 16 hexadecimal digits, if you will, here, okay? And the register, I mean, the destination can only be a register, so keep that in mind. And there's two other move instructions, which are used to copy from a small source to a large destination. and they are move z and move s. Move z means move and zero extent. Move s is move and sign extent. Okay, that means when you're moving from like a small register to a big register, like for example from, let's say, cx into edx, move z is gonna set the bits 16 to 31 at 0. Move s is gonna take the most significant bit of cx, so bit number 15, and copy that into all the higher order bits of edx. Okay, an example would be good, but not necessary. So you have all these different extensions to tell you that this is moving a byte into a word, this is moving a byte into a double word, this is moving a word into a double word, this is moving a byte into a quad word, and this is moving a word into a quad word. Now notice one thing is missing, which is moving a double word into a quad word. Actually, this is already something that exists, which is the move L instructions. Because if you noticed, you can move, when you do move L, the upper order 4 bytes are set to 0, and that's exactly what a theoretical move ZLQ would do. Okay, but move S actually has an LQ counterpart, and yeah, just sign extent. And there's also CLTQ, which is specific to EAX and RAX, okay? It sign extends EAX into RAX. Now next is the LEA instruction. Now remember how you had all the different syntaxes for the move instruction with the addresses and so on? Well, turns out that, okay, so move interprets this as an address and goes to that address, takes the data from there and puts it into RDX. LEA is simply going to compute this value, and instead of going to the address, it's just going to take the address itself and put it into RDX. For example, suppose RAX is 5, then this entire thing is 6 plus 5, which is 11. Move is going to go into address 11, take the value at address 11, and put it into RDX. Put that value into RDX. However, LEA is going to take 6 plus 5, 11, and put 11 into RDX. So you see the difference? And this is true no matter what specific syntax is used. All of these are in the same way. So if you're able to interpret this syntax with the offset and the base and the index and the scale, if you're able to interpret that well, you'll be golden for assembly, basically. Moving on to the next set of instructions, you have 4 unary instructions, which means they only take a single operand. You have the increment, the decrement, the negate, which, if you remember, for the integers, this was just the 2's complement, so flip all the bits and then add 1, right? And for not, it's gonna take the complement, which means just flip all the bits and that's it. Now, these also take the special syntax for the addressing, so that's a possibility. See, even this instruction for XOR takes that syntax with the base, the index, and the scale. Okay, so you have add, subtract, multiply, XOR, bitwise OR, and AND. Okay, that's about it for this lecture, but there's plenty of examples, and this one is some assembly code. It's asking which C code corresponds to this assembly. Now, if you remember, EDI had the first argument of the function, ESI had the second argument, and EAX is the return value, okay? That means we have 2 arguments here and a return value, so the function returns something. And just with using that information, we can already determine that because this returns an integer and it has two arguments, x and y, this is the answer because the other two possible answers do not have those qualities. However, let's take a deeper look at it. So it takes the second argument, which is ESI, and moves the value in ESI into EAX, and then it adds the value in EDI to EAX and stores it in EAX. Okay, so the add is basically EAX equals EDI plus EAX. Okay, and because EAX has the value of ESI, that means this is essentially EDI plus ESI, which means you're adding the two arguments of the function together, and the result is in EAX. And then you're gonna return with retq. And return obviously passes the EAX or RAX register back to the caller of this function. And that's what this function does. Moving on. Second example. You have the first argument, RDI. You go to that address and you move another 12 bytes. Then you take 4 bytes from there and move them into EAX, okay? So RDI is like a base, and you move 12 bytes, which is the size of 3 integers, if you notice. And that's put into EAX. So sum here is EAX, as the question here says. And you add to it, you move into it the value in array of 3, because like we said, we moved 12 bytes, which is 3 integers. So we started at index 0 basically, which is RDI, and jumped 1, 2, 3 integer sizes and put that into sum. And then we added the value at RDI pointed to by RDI. So RDI we said is the base, and it is just array of 0. So the value pointed to by RDI is array of 0, and we add that to EAX. So now we have int sum equals array of 3, and then sum plus equals array of 0. This is what the assembly is actually doing. It's equivalent, but that's what's happening. And then subtract the value at address RDI plus 18. Now 18 is hexadecimal, but in decimal this is 16. This one is a 16 and 8. So 16 plus 8, 24. 24 divided by 4, which is the size of the integer. That means address number 6, and that's array of 6. So you subtract array of 6 from EAX, so EAX minus array of 6, and store the result in EAX. So what this assembly does, if you were to convert it into C code, is int sum equals array of 3, sum plus equals array of 0, then sum minus equals array of 6, return sum. Next is a neat little command line utility called object_dump, which lets you take a compiled executable and disassemble it back into actual like assembly code, so you can look at what it actually does more easily. Okay, third exercise. What location or value in the assembly code above represents the C code's 6? It's an array of 6. Okay, so we said that array is like a pointer, and it holds and it's represented by RDI. and then parentheses RDI is the value pointed to by the pointer array, pointer, array, and that means array of 0. And then you add 18, which is 24, which means the 6th integer after array of 0, and that's index 6. And that's about it for this. Oh wait, right, there is a few more exercises here. So it's asking, based on this code, this assembly code, can you fill in the stuff that's in the C code? So you have int x, this is in RDI, int array, this is an RSI, and it's a pointer, okay? Keep that in mind. It contains, like, just array, which is RSI, is a pointer. It contains the location of something in memory. Then int I is in RDX, or EDX, if you will. Now, int sum equals, sum is going to be returned most likely. We can assume that that's going to be EX. So here EX, and something's being moved into it. And that's EDI. And EDI is the first argument. So int sum equals X. Okay? Next, sum plus equals array of something. And notice here, add is the plus here. And the destination is EX, which is, like we said, sum. Then array of. Array is the second argument, and that's RSI. And then we need to check the specific index that's being added to sum, to EX, okay? So RSI is the pointer array. I hope that was picked up. Okay, so I was saying that RSI is the second argument, which is the array pointer. Then RDX is the third argument, and it's going to be used as the index into that array times 4. And this 4 is just to say that these are integers, which are 4 bytes long. And so RDX is the specific index. So it's simply array of I. Okay? That means RSI, the pointer here, add to it I addresses. So from 0 you start 1, 2, 3, 4, however many is in I. And put that number, sum it with the sum variable. And then after that, we can return EAX with the ret instruction. Like it said, alright, I didn't actually cover this bit. Move SLQ, move and sign extend a double word into a quad word, EDX into RDX. This is like the CLTQ, except it's CLTQ is for EAX and RAX specifically. This is the more general form. So yeah, sign extend I into a folder register, then copy X into EAX and add array of I, and remember the 4 is because we're dealing with integers which are 4 bytes long, into EX and return. And that's the code. And sum equals X, sum plus equals array of I, return sum. It's kind of difficult to go from assembly back into C code if you're not used to it. I've probably not explained it too well, so it's hard to like put into words the thought process, but you have to look like back and forth at the different instructions. And that's why I more or less ignored this instruction, since it uses the third argument, and saw that EAX, I assumed that it would be sum, since that's the return value, and worked from there. So the add was used to check this, and the array is the second argument, RSI, indexed using the third argument, RDX, with scaling factor 4 because these are integers. Okay, next one. We have a pointer to an array and an integer. This is RDI, nums is RDI, and y is RSI. So move ESI. Okay, so this is ESI and this is RDI. Okay, because this is a pointer and this is an integer, 4 bytes. So move ESI, move y into EX. And then multiply nums of 0, because we're not adding anything to it, we're not using anything to index, we're only going to RDI, taking the value there, multiplying it by the value in EX, and the value in EX is, like we said, y. So nums of 0 times y. Next, subtract for the value at memory location 4 plus RDI, and since this is an array of integers, that means this is nums of 1, because 4 is 4 bytes after the the location nums, and that's the second integer of the array. So this is nums of 1 subtracted from EAX. Okay, and then shift arithmetic right. I don't think we've seen this this lecture, but anyways, shift arithmetic right by 2 EAX. So shift Z 2 places to the right. So this is a 2. Finally, return something. Well, this is an expression and not just a variable, because this says add 2 to EAX. So Z plus 2 is what's being returned. Okay. And if we check this, nums of 0 times y, Z minus equals nums of 1, Z shift right by twice, and then Z plus 2. Now notice that we loaded ESI, which is y, into EAX, which would end up representing Z. And then we multiplied that value by nums of 0 and put the result into Z again. So this was originally y, and then it decided to represent Z. So in assembly programming, because you don't have like an infinite number of names of variables to work with, you have to like juggle things between registers sometimes. This is a very simple example, but it can get much more complicated. And that concludes this lecture, I suppose. Okay, so moving on to week 6 and also week 7. Both of them will be on control flow. Week 6, actually, the lecture has a few things on arithmetic and memory, which we have already seen before. And because of that, we're gonna skip over those slides and focus on the control flow. So first thing to note is the registers that are in a typical x86-64 CPU, you have all the general purpose registers, REX through RDX, and these four special-ish registers, such as the stack pointer and the base pointer. And you also have these general purpose registers, R8 through R15. Then for the most special registers, you have the instruction pointer and the status register. And this status register gets a lot of attention when you have to consider control flow, because the bits in it, each individual bit has a different meaning. It's considered a flag for a certain condition. So for example, if the second bit of this register is 1, then a certain condition just occurred, and you can certain instructions check the value of that bit and act accordingly. So that's the main idea. We'll cover this in more detail below. So skip all that stuff we've already seen and go all the way here. So control flow, you've already seen this in high-level languages like C or C++. You have, for instance, this if statement. It performs a comparison, and depending on the result of the comparison, it's gonna execute either this statement, max equals x, or this statement, max equals y. Now, in the x86 instructions that we covered in previous lectures, it wasn't possible to do this. You could perform some bitwise masking or whatever to simulate the effect of a conditional statement, but you can only get so far. So there are instructions that actually let you do evaluate conditions and skip certain parts of the program entirely. And so there are two kinds of jumps. You have the conditional jump, which occurs only if a certain condition is true and goes to a different part of the program. And you also have the unconditional jump, which happens no matter what, without checking any conditions. So by having the condition checking instructions, as well as the conditional jumps that rely on them, and the unconditional jumps, you can implement if statements, while statements, do while statements, for statements, and switch statements. All of them are possible with just a handful of instructions. Now, remember the status register we talked about earlier. CF, ZF, SF, and OF are the names of 4 different bits in that register, and they're types of or instances of condition codes. CF corresponds to carry flag, ZF is the 0 flag, SF is the sign flag, and OF is the overflow flag. And yeah, like this says, you can consider them as if they are single bit registers, but the reality is that they are single bits of the same register. Moving on to the actual instructions that deal with them, you have compare and test. Compare sets all 4 of the mentioned flags. And what it does, it takes 2 arguments or 2 operands, source 1 and source 2, or A and B, and it sets the flags based on B minus A. Okay? Now, these are the exact conditions, but you don't really need to know them for the exam. I don't remember being asked about that when I took it last year. However, you will see later how you use this instruction in tandem with the conditional jumps, as well as the another conditional instruction called the set instruction. So the next instruction, rather than performing B minus A, is going to mask A bitwise AND with B, and it sets the flags ZF and SF according to that. Okay, this is the exact condition for when the flags are set to 1. Next, this is the first conditional instruction that uses the values of the flags there. And you have the jump, JMP, which happens no matter what. This is your unconditional jump. And the rest are all conditional based on the values of the flags or the condition codes. JE, for example, sets jumps if B minus A is 0, which would be only if B and A are equal. Hence, jump if equal. Okay. JNE is if they're not equal. JS means that B is smaller than A, in which case B minus A would be negative. JNS would be the other way around, non-negative. And you also have JG, which happens if B is greater than A. Notice the order. B is the second operand of the comparison, but it's the one that's being checked to be greater than A, okay? It's not A greater than B in this case, it's B greater than A. And the same occurs, the same is true for all of them. Then you have jump above, if above, and jump if below. Now set instruction, the set instruction is very similar, but except instead of jumping to a different part of the program, it's only going to set a certain destination, which is the only operand. It's going to set the value of that register to either 0 or 1 based on the value of the condition codes again. And it doesn't affect the upper order 7 bytes, only the lowest byte of the register. So again, set if equal, set if not equal, and so on. If equal, it's going to set to 1. If not equal, set E is going to set to 0. Set NE is going to set to 1 when when A and B are not equal, and it's going to set to 0 if they are equal, and so on with the rest of the instructions. Now here's an example of the compare and the set instructions in use. First, you need to set the actual flags using a compare instruction or a test instruction. And then after setting those flags, you can use the set instruction or the test instruction to which will check those flags. Okay, so it's a two-step process. First set the flags and then check the flags. Now we'll move on to chapter lecture 7, which covers more or less the same material, but in more detail. So we said that jumps alter they jump to a different part of the assembly program, and to do that, they need to alter the instruction pointer, which again contains the address of the next instruction to execute. So by altering that, the CPU will fetch a different instruction instead of the typical next instruction that should be executed. And that's what the jump instruction does. Okay, don't worry about this too much. We'll see it in more detail later on. So, in memory, well, I suppose what this slide is saying is that the lowest address is at the bottom and the highest address is at the top. And the text or the code, the assembly instructions or the machine code instructions are toward the bottom. They start from the bottom and the next instruction will be above that at a higher address. Anyways, so the first instruction is going to be this one, and the next instruction is this whole thing. Notice that these take a variable number of bytes. This one takes only 1 byte, this one takes 3, this one takes 7, this one takes 4, and this one takes 2. Okay. Now, when this is executing, the RIP is going to have the value of the next instruction to be executed, right? At the start, that's going to be 4004 ED, and while that's executing, the RIP is going to be set to EE, which is the start address of the next instruction, as you can see here. And then as that's being executed, RIP is going to be set to F1, which is the start of the next instruction, the following instruction. And this continues on. Now, you have the jump instruction here, which changes the value of the RIP and sets it to 4004 F8, and that's gonna be this instruction. So you see here, currently it's pointing at 4004 FC, and then as the jump instruction is done, it's gonna set it to F8. The important thing here is the arrow. This is a mistake in the slide, so ignore this. So the F8 part is gonna execute, and then you're gonna have the instruction pointer go back to FC, which is the jump, and the jump's gonna change RIP back to F8. F8 is gonna execute, then FC is gonna execute, which is the jump, and so it sets it back to there. And so the result intuitively is an infinite loop. You see? Next, there are two syntaxes actually for the jump instruction. The first is a label, which when you're programming in assembly is basically like a symbolic name for a specific point in the program. So you put a label at the start of the code, and then you can jump to that label afterward. And when this is assembled, the label is going to be replaced with like the label here is going to be replaced by an absolute address, which is the address at which you put that label in the first place. So it's a little bit of it makes it easier somewhat to write the programs because you don't need to know the exact location in memory. Now the other way is to put a star followed by an operand such as a register. I'm not sure if this can also take memory addresses, but anyways. So yeah, the jump instruction changes RIP, but you need to keep in mind the conditional jumps as we covered in the week 6 lecture. So like we said, step 1 is to perform a comparison or a test, and then step 2 is to perform a conditional jump which will check the values of certain condition codes, and according to those values will either jump or not. So again, here's all of those, and there's even more let's say instructions that do have the same meaning, so you only really need to memorize the ones on the left, but you can keep these in mind if you'd like. So yeah, like we said, when you have A and B, the greater than is relative to it's checking the condition whether B is greater than A. So JG is not checking whether A, which is the immediate value 2, is greater than B. That's incorrect. What it's doing is checking whether EDI, the B, is greater than 2, the A, okay? And the same is true for all the different instructions, although JE and JNE are symmetric, so the order doesn't matter. Yeah. These are the condition codes as we've seen before. This gives you a more clear idea of when they are set. And they're also set not only when you do the comparisons and tests, actually. They also occur when you perform additions, for example, as said here. And you have the carry flag just set whenever the unsigned value of t is greater or less than, sorry, the unsigned value of a here. And then you have the zero flag, which is if the result is zero, sign flag if t is negative, and the overflow flag, which happens whenever a and b are of the same sign, but t is not the same sign as those two, which means, for example, you add two negative numbers and you get a positive number, or you add two positive numbers and you get a negative number. That's what overflow is. Okay, now comparisons, yeah, we've seen that. You can apply them to bytes, words, double words, and quad words. We've seen this already. Test is, as we've seen, it performs the bitwise and does everything. Anyways, some exercises. Let EDI store 10, hex 10. Will we jump in the following cases? Compare 10 with EDI. So, and this is going to say jump if equal. If hex 10 and EDI are equal, then jump. And this is obviously a yes, because they are in fact equal, 10 and 10. And the second, test 10 with EDI. Now, jump if equal is going to check the what's it? Zero flag only, and the zero flag is set by the test instruction whenever the result of the bitwise AND is 0. In this case, the result is not 0 because the 10 here is in binary 10000, and this is also 10000. Bitwise AND, you have 4 zeros and a 1, and that result is not a 0, so this is not going to jump. See? Next, what is the value of RIP after executing the jump if not equal instruction? We first need to make the comparison, assuming, I think, again, that EDI is 10. So if 10 and 6 are not equal, then jump to 4004 DE. So the result, the answer should be C. And that is indeed the case. How can we use instructions like compare and conditional jumps to implement if statements in assembly? We've seen this more or less. I imagine you could put this together yourself more or less, but let's go through it step by step. In the C code, it says if the argument is greater than 3, then perform this statement. Otherwise, perform this statement. And this is the rest of the code after the if statement. Now, You perform the test, like a comparison in this case, and you jump to the else body if the test fails, if the comparison fails. That means, in this case, the opposite of arg greater than 3 is arg less than or equal to 3. That means you're going to perform the comparison and you're going to jump if arg is less than or equal to 3, which means you perform a comparison with 3 as the first source and arg as the second source. And after that, you're going to have a JLG, I believe. JLE, less than or equal. Okay. JLE. And that's going to jump to the else part. It's going to execute this the statement, which is the else body here, and continue to the rest. Now, if it doesn't jump, the following statement will be the body of the if, which is this statement. So if so you have the JLE, and it's going to jump to the else part, and it's going to execute that and so on. Now, if the JLE does not execute because arg is in fact greater than 3, then it's going to execute this. But it also needs a jump from after the statement to this statement, so that the return equals 0 here does not get executed. Okay. Now we have some reverse engineering. Compare. Yeah, this is exactly what we just did. It's pretty much the same code. So compare 3 with EDI, which is the value here. We assume it's arg. Then jump if EDI is less than or equal to 3 to this address. If this does not get executed, we move hex A, which is 10 in decimal, to EAX, which is the return. And so this is return equals 10. And we have a jump here from after this statement to this statement. As you can see, 4005x63 is the ret++. And now this jump if less than or equal to jumps to here, which is move 0 into EX, which is the ret variable. And so this is ret equals 0, as we saw before. Now here's another one. This is an actual loop. We've seen only the if statements. So how loops work is that they check the condition. Well, while loops anyway, they're gonna check the condition, jump after the loop if the condition is false. Otherwise, they're gonna execute the statements inside, and then jump to the comparison again. Okay. So it's gonna perform the comparison, jump after the comparison if after the loop if the comparison is false, and after that jump, after the jump statement, which means what's gonna be executed if the jump statement condition is not met, you're gonna have the body of the while loop followed by an unconditional jump to the comparison instruction again. So first move 0 into EAX, which is I here, and then jump to 40057A, and that's the comparison action. So this is another way to do it. What I explained was one way, and this is a different ordering of the instructions. So don't worry about it too much, both of them are completely valid. So we jump all the way to the comparison, which is below, We perform the comparison. Hex 63 is 100 in decimal. And if EAX is less than or equal to, sorry, this is 99. So if EAX is less than or equal to 99, then jump to 400577, which is the add statement. So it's gonna do this, which is the body of the loop, and then it's gonna check the comparison again, do the conditional jump, and so on until until this condition is finally false, in which case the jump will not occur and you will go to the return statement. And the slides do that again. It's gonna loop 100 times. And yeah, this is the general form of your typical loop. For loops and while loops are essentially the same. When it comes to for loops, they're just like a nicer format, a so-called syntactic sugar of representing this kind of while loop. And to be more accurate, you can also enclose this in a scope, because the loop variable doesn't exist after the for loop. So the more accurate would be to put the entire thing into a scope. And yeah, they have more or less the same assembly code, so don't worry about it too much. And that more or less concludes these 2 weeks, week 6 and week 7. You can remember the exact condition codes, but you probably shouldn't, because although they are instructive and they tell you exactly what happens at the level of like the status register, you don't need to know that because generally you can just check these values as well as the suffix here to know what actually is gonna end up happening. So yeah, that concludes these 2 lectures. Okay, so now we have the week 8 and 9 lecture on function calls and the runtime stack. The lecture slides begin with an example that extends the previous lectures on control flow. This example specifically is about switch statements and how they are implemented in the assembly language. So the idea is, you give it some value here, usually a character or an integer, and based on that value, you're gonna jump to different cases of the switch statement. The way this is implemented specifically is that the addresses of the codes of block 0, block 1, block n-1 of code, the addresses of these blocks are saved in something called a jump table. Target 0 is the location of code block 0, which is the assembly corresponding to block 0 here. Target 1 corresponds to code block 1, which is the machine code of block 1, and so on. And you use the value of x as a way to index into this array. So if x were 0, you can check this value. If x were 1, you check this value, and so on. Now, this isn't strictly correct because the cases might not necessarily be 0 and 1, it could be anything. But it's a pretty neat and intuitive way to represent it. So yeah, this is a more detailed look at this. So here's the jump table in memory. It has different jump statements. At index 0, for example, you have a jump to the default case because this switch statement does not have a case 0. Index 1 has a jump to case 1's code. Index 2 has a jump to case 2's code, and so on. And at the end of the case 1, case 3, and case 6 codes, you have the break statements, which are unconditional jumps to the code that follows the switch statement. Okay? So what you would do is you would load the value of x and you compare it against some value. If it is within a certain range, in this case between 0 and 6, you're gonna go using the jump syntax that uses the star operand that we've seen before. We're gonna use that to jump to a specific point in the jump table, and that point will have a jump statement to a different part of memory, which has the code for the actual case. And that's it. Moving on to the actual topic of the lecture. First, we need to understand what memory looks like for a running program. Okay, the program has some addresses starting at 0 and going up to some value. At the lowest addresses, you have the instructions, the machine code that has the actual code that gets executed. Above that, you have the literals, data that never change, such as strings. And you have the static data, such as arrays. All of these, the instructions, the literals, and the data, the static data, do not change throughout the course of the program while it's in execution. They are initialized at the start of the program. So the first thing that happens is that these are loaded into memory, and these are also loaded into memory in these specific locations. And the literals and instructions never change. Static data can change, however, their size does not change. So you can write to arrays, but you can't have arrays that change their size from, let's say, 5 elements to 20 elements. Okay? Above that, you have the dynamic data, which is known as the heap, which stores things that are only used in certain parts of the program and otherwise are deallocated. So temporary storage. And the way to put things into the heap in the C language is to use either the new keyword or the malloc function. Both of them work. Finally, you have the stack, which is a data structure that encompasses the last in, first out paradigm, let's say. So the bottom of the stack, which is the element that was pushed onto the stack earliest, is at the highest address, and the stack grows downwards. So as you push elements onto the stack, they're going to have lower and lower and lower addresses. The stack is used for local variables. So the x86-64 only has so many general purpose registers, 16 at most. And because of that, you don't really have enough space to contain everything you would like to work with. And so if you're working with more than, let's say, 14, 15, 16 variables at once, it would be good to put them onto the stack. The other thing is what's called here procedure context. What this means is procedure in this case can also mean a function or subroutine, whatever you want to call it. And basically this gives you like certain data associated with the caller of that function. For instance, after the function returns, where should it return to? What address is the instruction that should be returned to? What should be executed next after that function, you see? So yeah, the stack can be written to, but is not executable. It doesn't have any instructions per se. Then you have the heap, also writable and not executable. Same with the static data, because like we said, you can change the arrays, the values on the arrays, but not their size. And then you have the literals, which are constants, read only. And you can't execute them either. Only the instructions can be executed, and they are also read only. You can't have self-modifying code. So the star of the show here is the stack. Most of what we cover is about the stack. And so let's begin our study of it. The RSP register contains the address of the top element of the stack. Okay, so we said that the highest addresses have the bottom of the stack, the elements that were pushed onto there the earliest, and the elements that were pushed latest are at the top of the stack, and the RSP points there. And like we said, the stack grows downwards, which means the bottom has the highest addresses and the top has the lowest addresses. As you push more elements onto the stack, the addresses will grow lower and lower. Okay. So there is an instruction called push, which first decrements the value of RSP by 8, which is the size of a quad word. And then in the new location, it's gonna put this value into there. Okay, this can be a memory location, like a value at a certain memory location. It can be the value in a register or even an immediate value. It's gonna be put into this address. Okay, and then we have the pop instruction, and what this does is it takes the value that was pushed last, which is being pointed to by RSP. It loads that and puts it into whatever destination, and then it increments RSP by 8, which means makes it point to the previously last pushed element, because this one's been popped, so it's not part of the stack anymore. Even if the data is still technically present there, it's not part of the stack. So the RSP is pointing to the top of the stack, which is the previously pushed element that wasn't popped. And so, yeah, the popped element will go into the destination, whether it's a register or possibly a memory address. Now, when you have a procedure call or a subroutine call or a function call, whatever you want to call it, you have the caller and the callee. The caller can be itself a procedure, and it can be like the main of the program or some other procedure that's been called by main. The caller's responsibility, let's check here instead, is to save certain registers that it needs later. So for instance, it has some values that it wants to use after the function call, because the callee might mess with those registers. So the caller is going to save them to the stack, then it's going to set up the arguments of the callee in RDI, RSI, RDX, and even several other registers, and then it's going to call the actual function. And in assembly programming, this can be either an address or the name of the label corresponding to that address. Okay, now the callee is going to save certain registers that were not the caller's responsibility to save. So the caller only saves certain registers, not all of them. And which ones are saved is according to a certain convention. Okay, the callee saves the rest of them, and then it creates local variables. It initializes its own registers and functionality. It performs whatever computations and actions it might want to do. And it's going to set up the return value, which we have seen is in RAX, but RAX itself is just a convention. It can be any register. If you'd like. Then we have destroy local variables. So get these out of the picture, make them unable to interfere with the rest of the program. And finally, restore the registers that were saved in this step. And then you're going to return. And the return is going to check the address of this instruction, which was saved onto the stack, and it's going to return to that address. Now the caller is going to clean up the arguments, so it doesn't need them anymore. So it's going to get rid of them, replace them with something else, whatever it needs to do. It's going to restore the registers that it saved before the function call. And then it's going to take the return value from RAX, for example, and work with it in the rest of the program. Okay. So yeah, the callee must know where to find the arguments. So we have to have like a standard of which registers have which arguments. And it also needs to know where to return to after it's completed, right? The caller must know where to find the return value of that function. And since the caller and the callee run on the same CPU, they use the same registers. Both of them are interacting with those registers and saving and restoring and so on. Now, this general pattern has an example provided that follows it. We have two functions here. One of them is called multStore and the other one is called mult2. MultStore takes three arguments, x, y, and a pointer dest to a certain memory location. What it will do is call mult2 in order to multiply x with y, and the result will be stored in the dest location. Okay, so keep in mind x is in the register RDI, y is in the register RSI, and dest is in RDX. Okay, now let's see what happens. First, RBX is going to be pushed onto the stack, which is the save registers step of the program. Then it's going to move RDX into RBX. So it's going to take the destination pointer and save it into RBX register. And the previous value of RBX is still available to us in the stack. We just need to pop it later. Okay. Now, after we got this here, we're going to call the mult2 function, which is at address 400,550. Okay. And multStore, remember, had x in register RDI and y in register RSI. And it simply passed them into mult2 without doing anything. Okay, it didn't load anything because all the arguments were already set up in the first place. It didn't need to do any extra work to do that. So mult2 is going to take x and put it into RAX, and then it's going to multiply y by the value in RAX, which was x. So we have x times y stored in RAX. And then we're going to return. The return value again will be in RAX, and the return statement is going to take us back to the address after the call instruction, which is move q RAX, the return value, into the destination given by RBX. Okay, so we moved the third argument here, this pointer, to RBX, and now we're using that value and storing in the corresponding address the return value that was given to us by mult2. Finally, we're going to restore the value of RBX, pop it, and return. Now, although we saved the register and restore the register anyway. In a way, multi-store is actually also a callee of some function. And so it's actually saving the register RBX that was used by that function. But let's not confuse you too much. Just think of it as if it's saving its own register. Moving on. In general, when calling a function or a procedure, you're going to use the call instruction, as we've seen just now, and you're going to give it a label. Now, in this case, this was just given an address, but when doing assembly programming, you can give a label instead, and then give the label, write the label before that actual code, okay? Now, you need to, now the call instruction, what it's gonna do is gonna push the return address, which is this one, onto the stack. And later the return instruction here is gonna pop that address and put it into RIP. Okay. Yeah, like we said, the pushed return address is going to be this one, and it's going to be popped by the return instruction. So here's a more detailed look at what happens. So suppose the stack pointer RSP is pointing to hex 120 and RIP is pointing to the call instruction. The call instruction is gonna push this value into the top of the stack, which is the lower address here. So keep in mind these are all hex values and they're counting down by 8. So 130 minus 8 is 128. 128 minus 8 is 120, and 120 minus 8 in hexadecimal is 118. So don't let that confuse you. These are jumps by 2 and 8, 2 and 8. They are always by 8. So anyways, RSP is decremented by 8 to get 118. And then the address of the next instruction is saved onto the stack. And then the value of the RIP register is set to the address given by call, or given by the label that was written here if you're programming in assembly. So yeah, that's what happens. Now once you reach the return instruction, the return instruction is gonna pop the value at the top of the stack. It's gonna put it into the RIP register, and it's also gonna increment RSP by 8, so that the top of the stack would be back at 120. You see, the 118 entry is no longer there. It's not part of the stack anymore. And RIP is now pointing back to the instruction that followed the call. Easy enough. Now when it comes to the arguments and so on, the first 6 arguments of a function call are in RDI, RSI, RDX, as we saw. The 4th one's in RCX, 5th in R8, and the 6th is in R9. Now, if you have more arguments, you can actually just put them onto the stack, as seen here. But you only do this when you need to, because if you remember back in the week 1 lecture, as well as some later lectures in this course, the stack is in memory, and memory is very slow compared to the cache memories. Therefore, as much as possible, you try to it's slower compared to the cache memories, and especially compared to the CPU. So as much as possible, you try to avoid using the stack and keep your use limited to the registers. And finally, the return value is, as we know, in REX. Now, this is just a convention, so keep that in mind. Linux has a certain convention, and Windows, for example, has a different one. So moving on, by convention, values returned by the procedures are placed in RAX, as we know. And this is a convention, once again. It's arbitrary, could be any register. You could do anything if you want, but to keep things consistent between programs written by different people, stick to RAX. The caller must be sure to save the contents of RAX because the callee is going to change the value of RAX. It's going to assume that the callee changes RAX and the RAX will have the return value. So if RAX contains any important values that you will need later, save them somewhere, put them onto the stack, put them into another register, okay? Now the callee is going to put the return value into RAX, and that can be anything. If you want to return a value that cannot be put into RAX, for example, an array or a struct, then you're gonna need to return a pointer to that array or struct, okay? Upon returning, the caller finds the return value in RAX, and this we already know. And it's gonna use that value. It might restore the value that it saved before, and so on. So this is the same example that we saw. We already went over all the details, which registers have which arguments. Yeah. Now, what happens if we have several function calls nested and possibly even a recursive function call like this? This is like a tree representing the flow of the function calls. So function u calls who, function who calls am I calls itself to give this call, and this calls itself to get this call. After this, the condition is false, so it doesn't perform the recursive call. And then this second call is done, and that's this one. Okay, so first you call u, which sets the top of the stack to here, and the bottom of the stack frame, which we need to discuss, is set here. Now, u puts all of its values into here, so RBP is called the base frame pointer. And it points to the base of the current frame, which is kind of like a scope, as you studied in CSCI 112. And u is going to start pushing some values into this area, each time decrementing RSP. And then it might call the who function. And what that does is it's gonna set the value of RBP to point after the current value of RSP, and RSP is also going to change its value. So this is the base of the frame corresponding to the who procedure or the who function, and RSP is going to have its own who is going to have its own like RSP pointer with all the pushed values as pushed during the execution of the function. And then you have mi, the first call, which was done by who. Then mi is going to call itself, which gives you mi sub 2. And mi sub 3 is going to have that. Now, mi sub 3 is going to return without calling itself again. So we're going to return here. Now, this is still in memory, the mi sub 3, but it's not part of the stack anymore, as we saw before. And then we're going to return from mi sub 2 and mi sub 1. And then who is going to call mi again. And we're going to have the fourth call to mi in the same location. And so we're going to return and go back to the caller of u, which was here. That's like a general idea. I tried to give like a picture of what RBP and RSP do in this situation, but we'll see more of that later, I hope. Now, about the conventions, some of the registers are saved by the caller, and other ones are saved by the callee. And it is the caller's responsibility to save all that data in those registers before calling the callee, because the callee will assume that the caller already saved that data, and so it will just change it without uh, taking responsibility to save it by itself. And after the function call, it's going to restore the values as it needs and perform computations and so on, continue its execution. The callee saved registers are registers that were used by the caller, but it's the callee that's going to be saved by them, going to be saving them, sorry. Okay? It's gonna save those values in its stack frame, and the frame again is like this singular rectangle, or this one. And then it's gonna restore them before returning to the caller. So the full convention is given to you here. The important ones to know are RAX being saved by the caller, RCX through RDI, as well as R8 and R9 are the arguments, and they're saved also by the caller. R10 and R11 saved by the caller, and the rest are callee saved. The stack pointer doesn't really count anyway, since it's automatically manipulated by the call and the return instructions. And yeah, you don't need to actually push the values into the stack if you don't actually need them later. If you do, save them. If you don't worry about them. And that more or less concludes this lecture. I was hoping we'd get something more on the base frames and so on. Maybe in the next one, I'm not really sure yet. Yeah, that's it. Okay, so moving on to the week 9 and 10 lecture on optimizing program performance. There's a few important points at the start of the lecture slides before we get into the optimization techniques. First thing to keep in mind is that programs' primary objective, the main goal, is to give a correct output, okay? It has to function correctly. It doesn't matter how fast it is. If it doesn't give a correct output, then the program is more or less useless, okay? That's one thing. Now, when writing supposedly optimized programs, the first thing is to optimize at a high level by choosing an appropriate set of algorithms and data structures. This decision will be aided by your study in CSCI 215, Data Structures and Algorithms, as well as the following course for AI and Computer Science majors, which is Design and Analysis of Algorithms. You'll take a lot of different data structures that have interesting properties and may be adapted to certain problems that you might want to solve. Now, the second thing after this high-level optimization or choice, sort of, is that your code needs to be written in such a way that the compiler can optimize it into something efficient, okay? And we'll see in more detail what this means exactly with several examples. But just keep this in mind. The way you write your program will matter for the compiler. And because of that, you need to understand how the compiler actually works, more or less, what it can do, what it can't do with respect to optimization, and how to avoid any kinds of pitfalls that prevent it from doing optimizations. The GNU compiler collection has several levels of optimization that you can set according to these flags. -O0, for example, is the is more or less unoptimized. Dash O2 is the typical level of optimization. It performs most of the reasonable kinds of optimizations, not everything though, because there are some trade-offs. In the course, dash OG is used because it's more instructive than dash O0, because dash O0 uses the stack way more often than it needs to. Okay, dash OG will try to keep things to the registers as much as possible. Next, there are a few other levels of optimization. One of them is dash O3, which is faster than O2, but makes a trade-off by increasing the size of the final executable in favor of higher execution speed. You also have dash OS, which is optimized for size, and dash O fast, which goes so far that it completely disregards certain standards at times. The main thing for it is to just execute quickly. Some more points are when you are actually programming something, you need to consider two things, sort of a balance between how easy the program is to implement and maintain. So, how easy it is to understand what the program is doing at a high level and debug it and add to it, and sometimes. And on the other side, you have the efficiency or the speed of the program. So it turns out that most of the time, if you want to go full, if you want to go all the way on optimization, you're gonna do certain things to your code that make it more difficult to read or understand, okay? And also more difficult to debug or to extend, as it says. And so what you want to do is to try to keep the optimizations limited, well, your optimizations limited to a set few kinds of things and avoid certain other ways of writing the code that would interfere with your development. Of course, if your program actually needs to run as fast as possible, such as certain systems level programs as well as games, for example, then it's fine to go all the way with the optimization because that's your end goal. Anyways, so this slide tells you that performance isn't only at the high level with your choice of algorithm or data structure, because those do have like the big O or the big theta time complexities. But that's not everything, because these notations hide the constant factors from you. So different implementations of the same data structures or the same algorithms can have wildly different constant factors. Okay, so let's say a naive implementation written by a relatively inexperienced developer would run at, let's say, complete a task in 1 second. A more experienced developer who understands what the compiler does and how the system operates would be able to squeeze out more performance. According to this bullet point, can be as much as 10 times, but not necessarily. And so you have to optimize at multiple levels, not only the high level stuff, but also certain lower level things, such as the function calls, loops, and even statement by statement optimizations. Yeah. So you need to understand how programs are compiled and executed, which is the point of this course. How to measure program performance and identify the bottlenecks. You'll see a little bit of this stuff in the optimization blockers later in this lecture. But for the most part, especially the measurement part, is not really within the scope of the course. There are certain tools that allow you to identify where in the code gets the most, let's say, time, like which lines, which instructions are executed most often, and if you're able to reduce that in any way. And then this says how to improve performance without destroying the code modularity and generality, as we mentioned earlier. So the optimizing compilers, their job is to do some of these things. One of them is an efficient allocation of the registers. So some optimization levels, for example, might make more use of the stack, as we saw with O0. And this is very slow because you need to go to the cache memories as well as to the main memory at times. And more efficient optimization levels might keep things solely within the registers as much as possible and use them in different ways. For example, you might use less registers, keep the use of the registers, like keep things within like 2 or 3 or 4 registers instead of using all of the ones that are available to you. Or you can use more than the strictly necessary amount in order to not have to move things around between the different registers and so on, to save on several instructions. I hope that makes sense. Code selection and ordering. We'll see more of this later, but basically the statements in, for example, your C program, when it's translated into assembly, they might be executed out of order for efficiency's sake, and sometimes they might execute more time-consuming instructions in the background. So they're scheduled to run early, and while they're executing, all the circuitry is doing its job. The CPU is going to go through other instructions and execute those. And by the time the result of the time-consuming instruction is ready, the CPU will have almost reached the part of the program at which that result is actually needed. So it's gonna distance the part where the instruction begins execution and the part where the result of that instruction is actually needed. Third thing, which we will see later as well, is dead code elimination, which basically gets rid of any code that has no bearing on the final result of the program, essentially. And we have here eliminating minor inefficiencies. This is just a general point. So yeah, it's up to you to choose the algorithm, but the compiler will reduce the constant factors for you if you write your program well. And if you don't write your program well, you will introduce certain optimization blockers, as we mentioned earlier. And those include memory aliasing and procedure side effects. This one we'll see more later in this lecture. And when you have optimization blockers, the compiler will not be able to make optimizations, because if it makes a certain optimization to the part that has this blocker, then it's possible that in some cases the optimized code will have an incorrect result or output. And that's as this bullet point says. It will only affect behavior under pathological conditions. We'll see an exact concrete example later on. The rest is not really important. So these are all the different optimization techniques that we will see in this lecture. Let's go through them one by one. First is common sub-expression elimination. Given this code, A equals B plus C, B equals A minus D, C equals B plus C, D equals A minus D. Now notice B plus C is repeated here, and so is A minus D, right? Now you can replace this computation, A minus D, the second one, with B here, because you're repeating the same computation with the exact same numbers. The values of A and D did not change between this statement and prior to the statement. Okay? Now, you also have a B plus C and a B plus C here. However, this B plus C did not get replaced by A because the value of B was changed between the two statements. And so the value of B plus C will be different from the value of the same expression before this statement. And here you have the optimized code. Like we said, D equals A minus D is replaced by D equals B. Easy enough. Now, related is the shared common sub-expressions, in which you're given this code, up equals value of this index, I minus 1 times n plus j. Down equals the same, except it's a slightly different expression. Left equals another related expression, and right equals this expression. Now, if you expand this expression, you're gonna get I times n minus n plus j. If you expand this one, you're going to get I times n again, plus n, plus j again, okay? Then you have I times n again, plus j again, minus 1. And I times n once more, plus j once more, plus 1. And so, the shared common sub-expression, the sub-expression that appears multiple times, here is I times n plus j, okay? And so what you can do is calculate that only once, I times n plus j, and then use it with only subtractions or additions to get the final result of these different expressions. So this one becomes I and j, which is I times n plus j, minus n, to account for the minus 1 times n, and so on. And if you check the assembly corresponding to these two C codes, the left one has 3 multiplications for I minus 1 times n, and for I plus 1 times n, and for I times n twice. So that's 3 multiplications. And on the right side, because you multiplied I times n plus j only once, and used that value in all the other expressions, the assembly only had to do this multiplication once. Okay? Moving on to the next optimization, constant folding. This basically when in your C program or wherever else you have an expression that consists only of constants, instead of leaving that computation to be executed during the actual program's execution, you can simply evaluate this expression and replace it with its result during compilation instead of during the execution of the program. And this saves a few cycles at the very least. Division usually costs, let's say, 20 cycles. So if you don't need to perform this division, there you go, 20 cycles saved. You already have this floating point number directly available to you. You can load it as an immediate value into a register or whatever you like. The next optimization is copy propagation. Suppose you have two symbols, f and g. When you set f equals g, and then you use the value of f later, instead of using f, use g instead. That's basically it. So if you have x equals a, y equals x times b, z equals x times c, instead of x, replace it with the expression here, a. So you get a times b and a times c. Okay. The point of this is to reduce uses of x that are unnecessary in order to set up for the next optimization, which is dead code elimination. So notice that x is never used after these two, after this assignment. Okay, it's not used in this line nor in this line, and so because it's not used again, we can simply remove this assignment entirely, and we have just these two lines of code. Of course, if x is used later in the program or its value changes or whatever, then you can't perform this optimization. Just think about it for yourself and figure out like what kinds of things you can remove or replace as done here and so on. Anyways, code motion, this is more specific to a loop, though not necessarily. And it involves having a computation that is inside a loop, where this computation, its result does not depend on the result of it does not depend on the state of the loop. That means in every iteration of the loop, you're gonna get the same result for this computation. In this case, since this is gonna give you the same result every time, you can just move this out of the loop. So you do x equals y plus z, and then you have the rest of the body of the loop, which is in this case simply the I equals I plus 1 incrementing statement. And this is code motion. One thing to note here, some of these optimizations are set to be machine independent, which means you should they are done, or should be done at least, no matter what kind of processor, no matter what kind of architecture, and no matter the specific compiler being used. We've seen code motion already, so let's move on to here. We'll go over the previous slide after we cover this. Reduction in strength involves replacing a costly operation, like multiplication or division, with a shift operation or an add operation. So instead of multiplying by 16, you can shift left by 4 bits, and this has the effect of multiplying by 16, but is much faster. So this would take, let's say, 10 cycles, as given here. This would take only 1 cycle, so much faster. In Intel CPUs with the load effective address instruction, you can also perform certain addition like operations. And so you can, for example, add together copies of, let's say, 5 or 3 or 9. I mean, like, you multiply the number in a register by 3 or 5 or 9 according to the index offset or whatever. And you can do that in a single cycle as well. So let's say you have LEA RAX, comma RAX, comma 8. What this does is load effective address of RAX plus 8 times RAX. So that's 9 times RAX in a single cycle. And you put the result into whatever, some destination. So that's kind of convenient. Now, moving on to induction variable elimination. 1 second. This involves getting rid of the variable that is used to control the loop. So here we have I equals 1 while I is less than 10, t equals I times 4, and this is a mistake, it's I equals I plus 1, and that's the end of the loop. So the values of t are gonna be changing from 4, 8, 12, 16, 20, 24, 28, 32, and 36. But instead of doing this step where you multiply by where you set t to be equal to I times 4 and then you increment I, what you can instead do is simply make t as the loop variable. Okay, so you directly skip the step of incrementing I and multiplying it by 4 to give the result to t, and instead you directly loop on t and increment it by 4 each time, with the result, the condition being less than 40 instead of less than 10. I mean, this loops the same amount of times as this one because t is added by 4 every time, just to make that clear. Okay. Besides the two optimizations that act on loops, there are two others. One is called loop unrolling and the other is loop jamming. Skip all that. Loop unrolling. Basically, suppose you have this for loop here, which executes 100 times. And in each iteration, it's gonna call this function. In unrolling, you basically reduce the number of iterations, but you repeat the body more than once, okay? So in this case, it repeats 100 times. The unroll makes it iterate 50 times, but this gets executed twice. So in total, you get 100 executions of the function anyway. The reason this is considered an optimization is because the value of I is checked only 50 times as opposed to 100 times. And similarly, I is only incremented 50 times. So in this case, you save all the cycles spent on performing this comparison, spent on doing this increment, and also on the jump instructions to go back to the start of the loop and so on. Next is loop jamming, also known as loop merging. And this basically combines two loops together. So this loops 100 times, this loops 100 times. So in total, the values of I are going to be incremented and checked 100 times each. Instead, you can simply have a single for loop that iterates 100 times and performs the bodies of both of the loops. Let's read through this. To maximize the performance of a program, both the programmer and the compiler require a model of the target machine, specifying how instructions are processed and the timing characteristics of the different operations. So this is usually going to be in a certain manual or a reference for the processor. You can find those online somewhere, usually. And the compilers are designed according to these manuals. So as we saw with reduction in strength, we can replace multiplications with shift operations and add operations. So we saw that a single shift by some amount multiplies by a power of 2, right? This is always going to be faster than a multiplication. But suppose you want to multiply by some other number that is not easily obtainable with a shift. In that case, you're gonna shift and add both of them, okay? So you're gonna shift by, let's say, 4 bits to multiply by 16, and then you're gonna add by like add 3 copies of that to itself using LEA, scale index 2, and so you get a multiplication by 48. And is that going to be faster than a simple multiply by 48? It's gonna depend on the timing of information. Things like that. I mean, I bet the example that I used is still 2 cycles, way faster than the average multiply, but you get the point. Certain combination of shifts and adds can end up being slower than a direct multiplication, so multiplying is sometimes useful. And that's why you have a lot of techniques, a lot of interesting algorithms to compile things effectively, and as we mentioned earlier, allow instructions to execute in parallel, with slower ones being executed earlier and earlier than the results are actually needed. Stuff like that. Now, let's continue reading. Code optimization looks like a simple linear process of applying a series of transformations to the code in a particular order, but it's not usually the case. I'm not sure if the homework 2 this semester is the same as the one we got when I took this last year, but the assignment that we got involved a question where you have to figure out the order of the optimizations, like which optimizations were done and in what order. And because of that, we actually saw several optimizations being repeated in a certain way. So let's say I think 3 optimizations were relevant to that question, and they were repeated in something like the first optimization 1, 2, 3, and then the second optimization was repeated twice after that. Did that make sense? I mean, we had optimization 1, optimization 2, optimization 3. They could be any of the ones that we covered above, and optimization 1 was applied first, followed by optimization 2, then by 3, and then by 2 more iterations of or applications of optimization 2. And in different examples or different codes, you might get different orders or different optimizations being used, okay? And so a fair amount of trial and error experimentation is required to figure out exactly what are the best orderings of these optimizations. I'm sure there's algorithms that figure these out, but it turns out that you can't really do something that perfectly fits the program. Usually these optimizations are done at a more at a smaller scale, like within a function, rather than the entire program at once. Anyways, studying the assembly code representation of a program is one of the most effective means for gaining an understanding of the compiler and how the generated code will run. So try running gcc-og, and with the -s flag, excuse me, which will compile it only down to assembly level and not to machine code. Okay, check the generated code and then compare it with the dash s, again, assembly output of a different optimization level, such as dash O2. A good strategy is to start by looking carefully at the code for inner loops, identifying performance reducing attributes such as excessive memory references and poor use of registers. Starting with the assembly code, we can also predict what operations will be performed in parallel and how well they will use the processor resources. To novice programmers, it might seem strange to keep modifying the source code in an attempt to coax the compiler into generating efficient code. But this is indeed how many high-performance programs are written. So give it a shot. Try to check some of your bigger programs, let's say in C++ from your CSCI 112 and 113 projects, or even the smaller homeworks and so on, the labs. Compile them with the compiler, GCC, and check the output, see what modifications you can make and how they affect the assembly output. So yeah, compilers employ sophisticated algorithms and they give you some control over the level of optimization. Yeah. Next, we're gonna move on to the optimization blockers. Compilers must be careful to apply only safe optimizations to a program, meaning that the resulting program will have the exact same behavior that it would if it weren't optimized. So you have two different procedures here. One of them is incrementing the value at this memory location with the value at this memory location twice. So these are pointers to long variables. The variable at the location pointed to by xp is going to be incremented by the value at location yp, and that's going to be done twice. Now the second version of this function loads the value of at memory location yp only once, multiplies it by 2, and then increments the value at location xp by that value. Now, they seem to do the same thing, increment the value at star xp by star yp twice. However, the second version only needs to load this variable once, this value at yp. So it seems as though it seems as though this function is faster, but in certain pathological cases, this is not the case. And these pointers may actually refer to the same memory location, in which case you might get different behavior. Okay, so suppose the pointer xp and pointer yp are pointing to the same location. This is going to multiply the value at xp or the value at yp, the same thing, by 4, because you're adding it to itself, and then you're loading the value and adding it to itself again. So this is a multiplication by 4. On the other hand, if you load the value, multiply it by 2, and then add it to its to the original value, that's a multiplication by 3. So as you can see, it's possible that these two pointers, these two functions, have different behavior in the very specific case that these pointers point to the same location, and this is called memory aliasing. Okay, we have another example here. I'm gonna skip that. The point is that the compiler knows that it's possible for this thing, for this kind of thing to happen. And so if it is possible, the compiler isn't gonna bother optimizing the function, okay? So you would expect that this function is gonna get optimized to this one because you cut down by half the number of memory references you need to do. But the compiler will not do that because of the possibility of aliasing, okay? Another optimization blocker which we saw earlier is called the procedure side effects, where you have two functions here, three actually. Function 1 calls f 4 times, and f presumably returns some integer value, and function 2 returns 4 times the value returned by f. But suppose that f here affects a global variable, in which case this is going to affect the global variable 4 times, and this is only going to affect it 1 time. So if that happens, it's not possible for the program to optimize function 1 into a call of function 2. Does that make sense? And this is the case that was mentioned. If the function increments a global variable, you're going to get different behavior. Function 1 is going to increment the counter 4 times and return 1 plus 2 plus 3 plus 4 equals 10. And the second function is going to return 4 times 1, assuming these functions are called in a vacuum and not one after the other. Anyways, yeah, this function, f, has a side effect. It modifies some part of the global program state, changing the number of times it gets called, as in this case, changes the behavior of the program. So you need to be careful with that. Okay. There's a bit on the measurement of program performance, and that's cycles per element. And this tells you how many cycles are taken by a certain part of the program, I suppose. And what cycle means is it differs between processor to processor, and it depends on the clock which is inside the processor, which is, if we're gonna talk hardware, it's some kind of crystal, and it gives a signal at some constant frequency, which is actually very, very, very frequent at billions of times a second. And that's what it means for a processor to be some amount of gigahertz. It means the clock has a frequency of that many cycles per second. And that's why, in general, you don't want to consider things in terms of nanoseconds or picoseconds, and rather in terms of clock cycles, because the length of a clock cycle is gonna differ between machine and machine, but the number of cycles required to perform certain operations is not going to be too different. So here's a recap. When you're programming, what you want to keep in mind for yourself when in practice, yani, if you're doing something rarely and only on small inputs, do the simplest thing you can, okay? Don't bother with optimizing something simple or something that's rarely done. Now, if it's done a lot or done on very large inputs, use an algorithm that is that has a low big O cost, a low time complexity, if you will, and then just let the compiler optimize things for you. Now, only if your performance is really struggling or really low for whatever reason, then you're gonna check the assembly code and try to make the compiler perform better optimizations, or you're gonna check for certain optimization blockers, and you're gonna use profiling software to check where exactly are the bottlenecks of your program, and so on. So compiler optimizations may target one or more of static instruction count, dynamic instruction count. So static means the number of instructions, the number of times an instruction will definitely be executed. The dynamic count, which determines how many times they are executed as well, but this can differ between different executions of the same program according to certain inputs or the state of like some global state external to the let's say to the program itself. Okay, you can also target the cycle count or the execution time. Yeah, now processor speed. I believe I've already mentioned that it's not the only thing when it comes to performance. Like, yes, you want to limit the number of cycles and so on, but on top of that, you want to try to exploit the cache memory uh, of your computer. Okay? So there are several levels of cache memories, and you have the main memory and you have the disk storage. And the more frequently used data are usually in the caches here. The L1 cache especially. The L2 cache is like the next level, which has less frequently used somewhat data. L3 cache is slower, further away from the CPU, and much larger. Then you have the main memory and the disk. So you want to try writing things in such a way that the cache memory gets exploited somehow. Okay, try to keep things as small as possible and avoid certain sizes of your data, for example, so that they can fit within the L1 cache instead of going to the L2 cache, or within the L2 cache instead of going to the L3 cache, and so on. And caching depends on locality, which will be covered in more detail in a later lecture, but this gives you like an example to think about, where suppose your data is found in the cache 97% of the time. In this case, it takes only one cycle to get the data to fetch the data from the cache into the CPU. But suppose the data you want is not there, then you're gonna need to go to the next level. Okay? In which case, you're gonna spend more cycles, up to 100. And so the question asks, how much of your memory access time is spent on the 3% of accesses that are cache misses? So imagine this, a 97 hit rate. Okay? This means 97 cycles on these hits, and 3% take up 100 cycles each. So within 100 memory accesses, you have 97 plus 300. So 3/4 of your time was spent dealing with the cache misses. Therefore, you want to try as much as possible to make use of the cache. There is many resources out there telling you how to program in this way. It's not really within the scope of the course, but you need to understand that this is a thing. Some more questions you might have. The higher optimization levels are usually kind of hard to debug if you're gonna check the object dump or the assembly output. So when you check those executables, usually the machine code's doing something that is not quite easy to understand for you, because it was written by some guy who wrote a compiler that optimizes things really hard and does things in a way that you would not expect. However, it's kind of useful to learn, so go check it out anyway. Optimizations may not always improve your program. The compiler does its best, but it might not work, or it might even slow things down in some cases. Not always, but it can happen. Why should we bother saving repeated calculations if the compiler has common sub-expression elimination anyway? The compiler may not always be able to optimize every instance. So you want to try to keep things simple for yourself as well, and for other people who read your code. And you should, on occasion, try to perform this optimization yourself, because if you're repeating the calculation, like, it makes it seem as though there is something to gain out of that. But if there isn't, just do it yourself, okay? And so you will realize that, or people reading your program will realize that there's nothing new being computed. It's just the value that was computed before. That concludes this lecture. I suppose I spent too much time on this one. 49 minutes. That's all right. I hope I've explained that part well. Going into detail whenever I could. And any parts that you can that you have trouble with, you can always reference that specific part of it. Moving on to the week 11 lecture, we have the memory hierarchy. Here we have the storage technologies such as disk drives and random access memories. Then we'll take locality of reference, which is temporal and spatial locality. These were mentioned in the previous lecture very, very briefly. We'll study them in more detail in this lecture. Then we have the cache memory organization and operation. So how the cache memories, the different levels are all structured internally, and how to look up certain data in them, and so on. And finally, we have the performance impact of caches. So how the cache memories affect the actual performance of your programs. So random access memory, its features are it's traditionally packaged as a chip. The basic storage unit is called a cell, where one bit corresponds to one cell, and multiple RAM chips together form a main memory, or just a memory. Okay, so RAM comes in three kinds. The first is static RAM, which is used for your CPU registers and for the L1, L2, and L3 caches usually. Then you have the dynamic RAM, which is used for your main memory. And finally, you have the non-volatile RAM. The reason this is called non-volatile is in comparison to these two, which are volatile RAM. Okay? What volatility means is that the DRAM and SRAM, the volatile memories, they lose all the information in them whenever they are powered off. So when you power on, you need to move data into them somehow. Next, the non-volatile memories retain the value even if powered off. We have just mentioned that. And there's several kinds. The first is the ROM, the read-only memory, which is the data in it is programmed during the production of the memory. And then you have the programmable ROM, PROM, which is programmed only once. This separates the step of programming from the step of production. Okay, so this is produced once. So this is produced, and then at some point after that in the future, it's going to be programmed, and only once. Then you have the erasable PROM, which can be erased using certain techniques and perhaps written to again. And then you have the electrically erasable PROM, the EEPROM, which can be electronically erased. And this is the technology used for flash memories and so on, which allow for only blocks to be erased rather than the entire thing at once. Okay. Now the thing is that you can only erase a block up to 100,000 times before it wears out. And these technologies usually they track like which blocks are still not worn out and so on, but on average it takes about 100,000 erasings, and after a while, once enough blocks are worn out, you're gonna have to replace the memory. Anyways, the uses for non-volatile RAM include firmware programs. So the ROM technology is still used nowadays, usually for things such as the BIOS of your computer, the disk controllers, network cards, graphic accelerators, and security subsystems. All these things are hardware mostly that contains this specific data, and it's used for specific purposes in a predetermined manner. And then you have the solid state disks, your SSD, which is a pretty fast long-term storage. It's replacing rotating disks, which are the hard disk drives, HDDs. Still more expensive per byte, still somewhat smaller in most cases, but it's emerging. It's actually quite popular nowadays, but HDDs are still around. Anyways, and finally you have the disk caches, which are like basically a cache memory, but for the long-term disk storage. Useful when you have certain files that are more accessed more often than others. Now, we'll go off track slightly and talk about how the memory is actually used in practice. So you have the CPU here and you have the main memory here. They are connected through the system bus, IO bridge, and memory bus. And when the CPU wants to put, let's say, wants to find, no, wants to load a value from memory, and it knows which address that value is at. It's gonna place the address onto the memory bus, and that's gonna go through here, through the bus interface, through the system bus, through the IO bridge, and through the memory bus onto here. Okay, the main memory is gonna take that value and put it onto the memory bus, and that's gonna go all the way back to the CPU, and the CPU is gonna put the value into the register that it wanted to put it in. For writing, sorry, this goes kind of differently. First, the CPU puts the address onto the bus, same as before. However, the main memory is just gonna wait. It's not gonna take any value and put it onto the bus. Instead, it's gonna wait for the CPU to send the value it wants to write or store. It's gonna put that value into the bus, and the memory is gonna put that into itself. Next, we're gonna cover hard disk drives. They have several components. You have the platters, which are these circular things. You have several of them on top of each other, and they have a top surface and a bottom surface. Each platter has a top and a bottom surface, as shown here. Okay, and you have a spindle which allows the platters to rotate. You have several arms which extend above and below every platter. Every platter. And at the tip of the arm, you have the actual uh, reading and writing happening right here. Okay, so these arms are present above and below every single platter. So every surface of every platter has like an arm, a read-write head corresponding to it. Okay, and the arms are all connected together to a single actuator, which is gonna rotate and allow the arm to go like from here down to here and access any part of the platter. Well, this part anyway, and the spindle can rotate the platters to access like the different parts. For example, this bit. Okay. Now, you need to keep in mind that HDDs also have their own processor and their own memory. The reason is because given some address, they need to compute where is the physical location of that address so that they can navigate to it and send it over through the I/O bus. Now, the platters look like this. You have a spindle in the middle which rotates them, and the surface, every surface, top and bottom, each one is split into several tracks, and every track is split into several sectors, and the sectors have gaps in between them. The data is stored in the actual sectors, and if you know which surface, which track, and which sector, you can load the exact thing you want from the disk. And so let's go down here. The disk capacity is according to the number of bytes per sector, the average number of sectors per track, because the number can differ between the innermost tracks and the outermost tracks. And then you have the number of tracks per surface, the number of surfaces per platter, which is 2, and the number of platters per disk. So this is a more or less typical example that gives you 30 gigabytes. Kind of small, but whatever. So yeah, the arm rotates back and forth, and the spindle rotates the platters as well. And with that, you're able to access any track, any sector, any byte in any sector, and so on. Fairly simple. And because, yeah, the read-write heads, they are all attached to the same thing, they're gonna rotate all together, even if you only want to access a specific part of a single platter. Okay? Like they're mechanically joined together, so they rotate together. We've seen that. And when you want to check a specific part of the disk, the read-write head is gonna get into position, and then the spindle is gonna rotate the platter counterclockwise, and then you're gonna read this sector. It says blue here, but because I'm in dark mode, the color's inverted. Just assume this is blue. And so after that's read, suppose you want to read there. First, again, the read-write arm or the head is gonna move to the specific track that your requested data is on, and then the spindle is gonna rotate counterclockwise in order to get there. Now, what's being emphasized here is that this operation can take a while. This is a seek time, or a rotational latency, as it is called in this slide deck. And this time can take a while, so scheduling I/O operations with respect to the disk drives can be pretty important and almost vital for good performance from the disk. Okay, it doesn't matter how fast it actually gets the data out of there, it needs to also rotate quickly, and furthermore, it shouldn't rotate back and forth between different requested areas. It should try to get to them in such a way that it doesn't need to rotate as much and waste time rotating. This is extra information, so don't worry about it. So you have the seek time, which is the time that is needed for the read-write head to get to the correct track. You have the rotational latency, which is needed for the spindle to rotate to the correct sector. And you have the data transfer time, which is for the actual reading or writing of the data. Anyways, despite this weird circular structure with several layers, it's three-dimensional. It's usually better to represent it as something called the logical blocks. You can think of this like a really long array. And there is a mapping between this array, elements of this array, and the actual physical locations. And this mapping is controlled by the disk controller. And so whenever you make a request for a specific logical block, let's say logical block 2, the disk controller, which is inside of the disk, if we saw somewhere here, that's what's being mentioned over here, it's gonna take the logical block and convert it into a specific location relative to the surface, the track, and the sector. Is that correct? Yeah, surface, track, sector. Allows the controller to set aside spare cylinders for each zone, accounts for the difference in formatted capacity and the maximum capacity. Okay. Solid state disks are structured in a different way. They have multiple blocks, and each block is composed of multiple pages. Pages are of size 512 kilobytes at the maximum, and at the minimum 4 kilobytes. And the blocks contain 32 to 128 pages. You don't need to know the exact numbers, just know that these are powers of 2. That's the main thing you need to know. And when you read or write data, you need to do so in units of pages. So you read or write an entire page at a time, okay? And same as the EEPROM, the blocks wear out after about 100,000 operations. Whenever you write to a page, you need to erase apparently the entire block at once. Yes, modifying a block page requires all the other pages to be copied to a new block because you need to erase the entire block, and erasing an entire block takes about 1 millisecond, which is pretty long. Okay. The good thing about SSDs is that because they don't need to move around to seek, to rotate, and so on, they are faster and use less power, and whatever that means. And the disadvantage is that they wear out quite quickly. But the good thing is that this thing over here, the flash translation layer, which manages the addressing and the specific blocks and so on, it has logic that allows the writing and the raising and so on to be done across many different blocks rather than focusing on one block every time. So you spread out the wearing in such a way that you extend the lifespan of the SSD. In 2015, SSDs were about 30 times more expensive per byte than HDDs, but nowadays, nearly 9 years later, they're a lot cheaper, though still more expensive somewhat. Now for the CPU memory gap, it tells you basically that across time, the gap between the DRAM and the CPU has widened greatly. In 1985, they were more or less the same speed, and as time passed, the DRAM has gotten barely an order of magnitude faster, while the CPU has gone down 1, 2, 3, around 3 orders of magnitude, so like around 1,000 times faster. And because of that widening gap, you need to make use of the SRAM more than ever. So that the performance of your programs doesn't suffer too much. And the way to do that is to make use of a concept called locality. Now, this is a general principle, almost a rule of thumb in a way, where programs tend to use data and instructions with addresses near or equal to those they have used recently. The near part refers to spatial locality, and the equal part is referring to temporal locality. So, temporal locality is the part where recently referenced items are likely to be referenced again in the future. So, suppose you access some memory location, you're likely going to access that memory location again, let's say to write to it after reading from it, and something like that. Not necessarily the case though. And then you have the spatial locality, in which items with nearby addresses tend to be referenced close together in time. And this means suppose you accessed this address first. This one's going to be loaded into the cache. And so when you want to access this one, it's already going to be there for you. And similarly with the temporal locality, I didn't mention the cache there. After you access this one for the first time, it's going to be put into the cache, so that when you access it again, say to write to it, it's going to be there already for you in the cache. And then you can just write to cache and continue. And the cache will later transfer to the main memory if needed. Okay, so this is an example of locality in which you have data references referencing the arrays, the elements of the array. And this is spatial locality because every time you're accessing different parts of memory, but all of them are very close together. They're just integers one by one in very close, a contiguous memory region. And then you have the referencing of the variable sum in every single iteration, and this is the same exact address every time, being accessed multiple times, and that's temporal locality. Similarly with the instructions, not just the data, but the instructions of the machine code of the compiled program. The instructions are also data in a sense. They are stored in memory, right? So you have two two dimensions to the locality here. The first is that you're referencing instructions in sequence. So you go by instruction 1, instruction 2, instruction 3, and you're not jumping around between instruction 1 and instruction 1001 and then back to instruction 500 and then instruction 1 again. No, you're sticking to instructions that are very close to each other. Okay? Second thing is temporal locality, in which you're repeating the same instructions over and over again. So they're going to be put into the cache to improve the performance of the program, because you only need to load those instructions into the cache once, which takes some time, but after that they're going to be there for you to access quickly. Okay, and to load from the cache into the CPU again. Okay, now moving on to the memory hierarchy. uh, there's a few important concepts that have been true for God knows how long. First one is that faster storage technologies tend to cost more per byte. They have less capacity and they require more power. This is especially the case for SRAM. And other than that, the gap between CPU and main memory is widening. We've seen that in the diagram above. And finally, well-written programs tend to exhibit good locality. One second. So well-written programs are that exhibit good locality. Basically, they're going to be able to make use of the cache memory because they're not jumping all around the place and accessing different points. They're sticking in the same part, so things only need to be loaded from main memory once instead of several times. And that makes them very fast for one, but also other things. And based on these properties, there is this thing called the memory hierarchy, which basically gives you a good mental model for how these things work. So at the top you have the registers, then you have the L1, L2, and L3 caches, as you know. You have the main memory, the local disk, and remote secondary storage. And you've seen all of this, I believe, in maybe lecture 1 of the course. So it's nothing really new to you, but you need to understand that near the top, these things are more expensive, smaller, and faster. And near the bottom, they are less expensive, they are slower, and they are larger. And they also require possibly less power. It depends. Like the SSDs don't need as much power as HDDs, as we've mentioned, while the registers and so on, they consume a lot of power. Anyways, so the cache memories, what are they exactly? They are a smaller, faster storage device that acts as a staging area for a subset of the data in a larger, slower device. And the thing about the memory hierarchy is that each level of it is like a cache memory for the one below it. Okay, so the L3 cache is a cache for the main memory is a cache for the secondary storage. So for example, if you're writing to a file, the file will actually be stored in the main memory, and once you finish writing to that file and you close it, the data in that file that is in main memory is going to be put in the place of the copy that is in the local disk, something like that. So this is called a staging area. If you've used Git before, it's a similar idea. Then why do memory hierarchies work? Because of locality, programs tend to access the data at level k more often than they access the data at level k+1. We've seen this. And because of that, the lower level memory can be slower, and we can yeah, it can be slower because we're not using it as often, so a speed up wouldn't benefit us as much as if we'd sped up the higher levels of the hierarchy. Make sense? And here's a table that tells you the types of caches almost, what's being cached, where it is located, how long it takes to fetch the data, and what manages it. Okay, these are some examples. You don't really need to know them, but it's good to have this information in your head. Now, how does the cache actually work? So the memory has all these different blocks, let's say 0 to 15. and the cache memory contains only a few of those blocks. It doesn't contain byte by byte the certain like bytes all around memory. No, it contains entire blocks from the memory. So don't let that confuse you. Now, a cache hit is when you request a certain address in memory, and the address or the block containing that address happens to already be in the cache memory. In that case, it's going to be a hit because the cache can directly return that data back to the CPU or whatever. On the other hand, if you have a miss, the cache will not contain that block, and so it's going to request it from the main memory or from the next level of cache, and the main memory is going to load it back into the cache memory, and then the cache is going to serve it to the CPU. There's two things to keep in mind here. There's a placement policy, which is when you're storing a certain block in the cache, where do you put it? And the second thing is replacement policy, which determines which block gets evicted. So which of these blocks, 8, 9, 14, and 3, is the least likely to be used here? The cache memory in this case decided that it's 9, so it replaced 9 with block 12. So yeah, we've seen this already. And there's an additional here cache memory, which I think was this diagram exactly was also in lecture 1, but keep in mind the cache memory is actually inside the CPU chip, okay, and that it is SRAM. Next we have the general cache organization, which is basically how the cache memories are actually structured. Generally they have, let's say, some number of sets, and these are sets of things called lines. And these lines, what they are is basically they contain 3 components. One of them is the valid bit, the tag, and the actual data, which is the blocks that we mentioned up here. Okay. Now the valid bit basically tells you whether the block is actually up-to-date data, basically, whether it's still whether it's like it matches what's in the main memory. Then the tag contains certain information that is needed to actually find this specific line in the cache. Okay, so suppose you want to find a certain word or a certain value in the cache. What you're going to do is you're gonna check which set contains the line that you want, and you're gonna find that line using the tag here. So if the tag matches and the valid bit is 1, so if it's a valid line and the tag is matching, then you're gonna check the offset here, and the offset tells you where in the block is the actual data that you want. Okay, so here's an example that is simplified so that sets only contain 1 line instead of some power of 2. And let's say you want to find the address of something. First you get the set, which is set 1 in this case, and you check whether the address not the address, the tag actually matches the one in that line, and whether that line is actually valid in the first place. If it's valid and there's a match, then you have a hit, and you're gonna check the specific address here given by the block offset. I hope that's accurate enough for our purposes, but if you need more details, be sure to check the book. Now, the cache performance is determined by a few things. You have the hit rate and the miss rate. So, how many of the memory references are actually found in the cache, and how many of them are not in the cache that you need to go all the way to main memory to check. And the miss rate, which is how many of them are not in the cache, is typically between 3 to 10% for the L1 cache, and less than that for the bigger caches like L2 and L3. Okay. Next, you have the hit time, which is how long it takes for the cache memory to deliver that line that we mentioned here back to the CPU. Okay. And that includes the time to determine whether the line is in the cache in the first place. So the time to process this thing and find the specific line in the specific set and get the data from there, that's all counted as part of the hit time. Okay. You don't really need to know the exact numbers, but the L1 cache might take, let's say, 4 clock cycles, and the L2 cache might take 10 clock cycles. And then the miss penalty is how long it takes to get the data from main memory. So because you didn't find it in L1, you're going to check in L2, not found, check in L3, not found, go to main memory and check. And that's going to take as many as 200 cycles. Now, how do you write code that makes use of the cache, also known as cache-friendly code? You want to minimize the number of misses in the inner loops, which means like the inner loops are those that are yeah, inner loops are the ones that are like run the most times across the entire program. They're kind of hotspots of the program's execution. So when you're in them, you want to try to keep the temporal locality and the spatial locality in use, in the sense that you reference the same variables, and when checking arrays, you're checking like adjacent indices instead of like jumping like the by every other 2 indices or every 12th index, 12th element. Jumping around is really bad for the cache because it contains entire blocks and not bytes or words. And so keep things within like the boundary of a single block. Okay. And that way you're gonna keep the misses as little as possible, as few as possible. So to summarize, cache memories have a significant performance impact, like we just discussed. Focus on the inner loops. Try to maximize spatial locality by reading data objects with sequentially with stride 1, which means indices increase by 1 every time, every iteration, instead of by 2, by 4, by 8, or whatever. And you maximize temporal locality by using data objects as often as possible once they are read from memory. So once you read something from memory, don't keep it around until without using it until way later. No. Use it often and keep it loaded so that it's available in the cache whenever it's used, okay? That way you're gonna exploit the temporal locality and get the most out of your cache memories. The speed gap between the CPU, memory, and mass storage continues to widen. We've seen that in the graph. Well-written programs exhibit a property called locality. Memory hierarchies based on caching close the gap by exploiting locality. And that we've seen already, as we know. The higher levels are are smaller, and they contain the more more frequently used data, while the lower levels are larger and slower, so they contain data that is less frequently used. That concludes this lecture. A complimentary cough to end this recording. We're moving on now to the final lecture of the course, which is on virtual memory. So what are processes? Processes are running instances of programs. What are programs? Programs are just the executable files that are present on your disk. When you click them to execute them, they're going to be loaded into the main memory. The registers of the CPU are going to be initialized and it's going to start executing. When it's executing, that's a process. Okay? Now, the idea of a process, the understanding that this is a thing, gives you two important abstractions. The first one is logical control flow, which is the idea that every program or every process, sorry, seems to have exclusive use of the CPU. It doesn't care about what the other processes are doing with the CPU. It just thinks about its own use of the CPU and the registers. The second abstraction is that of the private address space. Each program each process again, sorry, seems to have exclusive use of main memory, okay? Now, the logical control flow is enabled by a thing called context switching, which is provided by the operating system kernel. And the private address space idea is provided by the kernel mechanism called virtual memory, which is the main topic of this lecture. We'll see a little bit more about context switching before we actually get into virtual memory. Now, what is a process? Again, we've seen the actual definition, but let's see it more concretely. So every process has its own copy of its own view of main memory, which has a stack, a heap, some data, and the code, which is the instructions, machine code instructions, right? And it also has the values of the registers as it is currently executing. And this process, in this case, is being executed currently by the CPU, okay? Now, the other processes, they have also their own copies of the stack, the heap, data, and the code. But they're also going to have their own set of registers. Now, this set of registers isn't in the actual CPU. It's currently stored in the main memory because this process is not being executed by the CPU. The CPU is busy with process 1, okay? The CPU later might move on to process 2. It's going to load the values of the registers from here into the CPU, and it's going to start executing. Once it's done with this process, it's going to save the registers back into here and move on to the next process. And here we have the actual programs, which again are the executable files, like we said. So yeah, that's more or less everything for a general picture. You also have the operating system kernel, which is basically like its own process, but it has a few additional privileges and so on to allow it to manage all the other ones. Okay. Now, multiprocessing, which is the idea that you have several processes running simultaneously, okay? What seems to be the case, the illusion, is that every process, this is process 1, this is process 2, and this is process n. What seems to be the case is that each one has its own copy of the CPU, its own address space, which has the stack, the heap, the data, and the code. And process 2 has its own CPU with its own set of registers and all of this, right? This seems to be the case, but the reality is that there's only one CPU, right? And so what happens, which we'll cover context switching now, how the CPU switches from one process to another. So it's currently executing this process. The dotted rectangle here refers to the address space that is being managed right now. Okay, the address space is basically the set of memory addresses that the CPU is currently allowed to access. We can put it in that way. Okay, and so it has the registers, it has a stack, the heap, the data, and the code. And then suppose it wants to move on to this process. Okay, what it's gonna do first, it's gonna save the registers that are in the CPU and put them into memory in this predetermined location, which is the saved registers. And then it's gonna move on to this process, change the address space to that of this process, and then it's gonna load the registers from here into the actual registers, right? From memory into the CPU. Okay, that's a context switch. Now, this is only one CPU, and this was the reality 20 years ago, or even more. Okay, the modern reality is that you have several CPUs, each with their own set of registers, and each one executing some process. Okay, and these are the CPU cores that you probably have heard of. However, there's usually more processes than there are CPU cores, so even still, the cores will be context switching between the processes, just not as often as if it were with a single CPU. Okay, so the advantage of the multiple cores is that several processes are being executed in parallel. This is the parallelism that was mentioned in week 1, I believe. And then concurrency is just, let's say, this stuff. So this is concurrent but not parallel because we have several processes executing in an interleaved manner, and only one is executing at any given point. And then for the parallelism, you have several cores, each one executing a a process. So that's some linking of the concepts that you've seen. Now we move on to the more detailed look at virtual memory. Like the warning says, it's fairly complicated, but it's really important, so you've got to understand it. Now, in previous lectures, we've always referred to memory. No, what we've referred to as main memory is actually just the virtual memory, okay? We have all these addresses from zeros up to Fs. This is 16 Fs and this is 16 zeros. That means from address 0 up to address 2 to the 64 minus 1. And this is a huge amount, okay? I mean, 2 to the 64 addresses, that's this many bytes, okay? Now, we certainly don't have that amount of space in physical memory, especially for every single process. But in virtual memory, every process seems as though it has this amount of space available to it, okay? Now, the first problem is, yeah, how does all of this fit into a smaller physical main memory that encompasses like 8 gigabytes worth of addresses? And this is only for a single process, right? So we have several hundreds even of processes that each have this many addresses available to them. So how do we fit all that? The truth is that not all of it is used, obviously, and there is some kind of mapping between the virtual addresses to the physical addresses. We'll cover some of that in this lecture. Now, the second problem is memory management, okay? So we have all these different processes. Each one has its own set of stack, heap, text, and data. And so where do we put that into the physical main memory? And that's a related problem to the first one. And we have two other problems which are on how to protect main memory. So suppose this part of main memory is allocated to process J, okay? And process I has its own location in memory, but it wants to access the memory allocated to process J. It should not be allowed to do this, okay? So if it tries to do this by accessing some address that is out of its allocated space, then we should prevent that. We should not allow it to happen, especially modifying the data. And then we have sharing of areas or regions in main memory, in which the operating system basically sets up like a shared memory region in which both processes can use the data in this region, and each process also has its own private, like exclusive part of part of memory that it contains its own stack and heap and so on. Anyways, how do you solve the problems that are above? It's all just virtual memory. Like the specific details will give you solutions to all of these, I hope. So, what we saw before is that what we assumed to be the case, at least, is that the CPU generates a physical address when it wants to access some part of memory, and the memory directly returns the data in that address to the CPU. But what actually happens is that the CPU generates a virtual address corresponding to a location in a certain process's virtual address space. So let's say this address. And then you have something called the memory management unit. And the memory management unit is going to take a look at this and map it to a certain physical address on the actual physical RAM, okay? So it takes a look at this. It realizes it belongs to, it refers to a specific location in the main memory, the physical memory. And so it's going to go to that location that corresponds to this one, this virtual address. And it's going to take the data there and give it to the CPU, okay? That's the basic idea. And now, the benefits of virtual memory is that it isolates processes, which means they each have their own address space. And so address 40308 on process 1 refers, let's say, to this address, but virtual address 40308 on process 2 can mean a different physical address. Let's say hex 1308 instead, okay? So the same virtual address in two different processes has a different can have two different meanings, two different corresponding physical addresses. And this is kind of useful because the processes don't need to worry about interfering with each other's addresses, like their own allocated memory space. Okay. Next, we have simplification of memory management because each process gets a uniform address space. Okay. Now, we get into more detail about each process's view of the main memory. And actually, all of these addresses are unused. At addresses starting at 400,000 in x86-64 anyway, you have the code, the machine code instructions, the .text, as we say. And following that, we have the read and write data, the static data and the literals within the .data section. And both of these are loaded already from the executable. So everything here is already present in the executable file, okay? And then we have the heap, which has the dynamic data, as we mentioned, and the new keyword in C, as well as the malloc function, give you allow this heap to basically expand and grow outwards, okay? And the BRK, whatever that is exactly, whatever that stands for, seems to point to the top of the heap, or like how much is allocated to it, more or less. You also have shared libraries, and these are basically like the this stuff here. The shared libraries can be certain code, certain like functions that are in dynamically linked libraries, and these can be accessed by two different processes, even though they're only loaded once. So this is a mapping of like shared memory in a controlled way, okay? Hope that I was able to explain that well. Finally, we have the stack, which begins at the high addresses, 7 followed by how many steps? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 Fs. So this is 12 in total, and 12 hexadecimal digits is 48 bits, like we said. Anyways, so the stack begins at this address and expands downwards with the RSP register pointing to the top of the stack, and we've already taken that. And the rest of the address space from 8000000000000 up to all Fs is taken up by the kernel virtual memory, which is inaccessible to user code. So this program over here cannot access these addresses. Anyways, allows memory content to span devices. So this means you can have several RAM chips, you can have several disks, several HDDs, SSDs all together, working together, and virtual memory basically allows these to be mapped to in a way. So we've seen already the memory hierarchy, and the virtual addressing allows you to access everything between the registers down to the secondary storage. Here, usually this has something to do with swapping of processes and so on, which I think we'll see a mention of later, which relates to a concept called thrashing. Anyways, so the registers are on the order of tens of bytes and take 0 cycles to access. The L1 cache has on the order of tens of thousands of bytes, takes 1 cycle to access. Then you have 100,000 bytes with 10 cycles for the L2. Millions, billions of bytes, hundreds of billions of bytes, and tens of trillions of bytes here. Anyways, the virtual memory as a cache, okay? Now, we took before the blocks and the cache misses and the cache hits and so on, right? When it comes to virtual memory, instead we use the term page and page fault instead of cache miss, okay? And we have page hit, I believe. I'm not entirely sure. I haven't read down there yet. Anyways, so the page size typically ranges between 4 kilobytes up to 64 kilobytes. And this is fully associative in the sense that there is a mapping, I suppose, between the virtual memory and the memory. And the replacement of the pages in virtual memory is not necessarily the least recently used, like we saw in the previous lecture. There can be more complicated rules according to what processes are using what and so on. And finally, write back as opposed to write through. We haven't really seen this concept, so let's just move on. Now, address translation. How do you translate from a virtual address, like 40308 as we saw, down to a physical address, like 308? As we know, these take up n bits, and so the address space size can be up to 2 to the n bytes. And what happens here is that this virtual address actually has two parts. The first one is the page number, so which page is the data in, and the second is the page offset, which is where in the page is the data in. Okay, so which specific byte of this page is the data in. And the MMU takes this virtual address and, using the page table, maps it to a physical address. And the physical address also has something like a page number and a page offset. And notice, the offset on the virtual address and the offset on the physical address are the exact same. Okay? It's only the page number that will differ. So this is a nice trick to deal with the mapping. You only need to map the page numbers to each other, and the offsets can be used without worry. Anyways, the page number and the virtual page number and the physical page number are mapped in something called the page table. The virtual page number is used as the index to the page table, and the page table entries contain two things. First is whether the cached entry is valid, and the second is the corresponding physical page number. Okay. And also, to answer the question of where is the page table in the first place, we have something called the page table base register, which contains the address of the page table, a pointer to it, easy enough. And every process has its own PTBR, and so this is one of the things that are saved by the kernel whenever it performs a context switch. Okay. Now, if the page table entry is not valid, you get a page fault, which is essentially a cache miss. Same idea. Okay. Now, if it is valid, it's gonna check the page number and give you the physical address of the data and take that from memory into the CPU and so on. Now, the size of the table depends on the size of this field. So the page numbers, let's say, are, okay, you have n minus p bits used for the page number. And so 2 to the n minus p is going to be the size of the table, because you have n minus p bits, and so those differentiate up to 2 to the n minus p entries of the table. And finally, you have the multi-level page table. And in this case, you actually have smaller page tables in which each one is like basically a virtual page number and used to index one of the page tables. And what happens is the entries in the first few page tables are going to be just pointers to the next level, and the final level will actually contain the physical page number. Okay. So you would take the first VPN, virtual page number, use that to index into the level 1 page table, whose location is indicated by the page table base register. And then the entry in that level 1 page table is going to point to the level 2 page table. There can be multiple level 2 page tables. And then you're going to take the virtual page number 2, use that to index into the second page table, and so on up to level k, the final page table, and that's gonna have the actual physical page number. Now again, this is only gonna take up to n minus p bits, so there can only be so many page tables, okay? Usually you stop at 2 or 3 levels. I believe Linux has up to 3 levels. Now let's do a few examples. The first is on the page hit. Now remember this diagram from several slides ago. We're gonna see in more detail how the memory management unit actually gets the physical address of the data that the CPU wants, okay? Based on the discussion that was given above. Now, the memory management unit is gonna take a look at the virtual address. It's gonna extract the virtual page number and use that along with the page table base register to find the specific entry of the physical page number. So it's going to use that to check the main memory, and the entry is going to be returned to the memory management unit. This entry contains the physical page number. And now the main memory management unit is gonna check the page offset now, along with the physical page number that was returned from the page table, and use that to access the physical address of the data that the CPU requested. And so that data is going to be returned directly to the CPU. Now, we have another scenario here with a page fault. So the CPU again generates a virtual address, and the MMU uses the virtual page number along with the page table base register to index into the page table and get the entry. Okay. Now the MMU is going to realize that the entry is invalid through the valid bit. And so it's going to interact with the page fault handler. And what this does is going to go to the disk, because the main memory is just a cache for the disk, okay? And it's going to tell the disk basically to load that data, that requested data, into the main memory and give me the physical address of that in the main memory, okay? So the disk, we assume, loaded the data into the main memory, and we now have the address of the data that was loaded just now, that was originally requested by the CPU. And so the physical address here, the physical page number, is given to the MMU, and the MMU uses that along with the page offset again to get the physical address and finally give the CPU the data that it requested. Okay. Now, normally disk operations are very, very slow. Well, not normally, they always are, even if you have a disk cache. But it's fine if you have good locality, because this will happen only once, and the data and the rest of the block that was loaded is already going to be in the main memory or even in the higher level caches. Okay, so that's very good. Another concept is something called the working set, which are the pages that are currently being used by all the processes together. And if the working set is larger than the entire physical memory, you're going to have something called thrashing. And thrashing basically is when you have so much data to work with that you have to keep loading things out of the main memory and back into the main memory over and over again. And this is really bad. It damages it wears out the devices faster than you would expect. And so don't run too many processes at once, will you? Okay. Another thing is that we have actually another cache memory that is specific to the address translation that we've seen, and it's called the translation look-aside buffer. Okay. Now the the memory management unit normally is going to go all the way to the page table and get the specific page physical page number and then go back to the main memory again. The translation look-aside buffer is going to store a few recently used virtual addresses, virtual pages, or virtual page numbers, sorry, and their corresponding physical page numbers. And so when the memory management unit encounters a virtual page number, it's gonna check with the TLB first. Is that page number in the TLB? If so, the TLB is going to return the corresponding physical page number, sorry, and the MMU is gonna use that along with the page offset to index into the main memory and get you the data. So it's only a single access of the memory instead of going back and forth with the page numbers and so on. And that concludes this lecture. I believe there is like some cache exercises or something. I'll take a look at those, and if they're worth solving, I will. Otherwise, that concludes this revision video. Thank you either way, and goodbye.